Okay, good afternoon, everybody, and good morning, good evening to all of our guests online from around the world. My name is Mani Sarathi. I'm an associate professor here at KAUST in the Department of Chemical Engineering and working in the Clean Combustion Research Center. So thank you for joining us on this second day of the conference about near zero carbon combustion technology. So this session is having 4 invited speakers followed by a panel discussion. And the focus of this session is actually about not near zero, but really zero carbon combustion. And zero carbon in the sense that the fuels that we'll be investigating, the combustors that we'll be talking about in this next session are carbon free, entirely driven by ammonia, which is nitrogen and hydrogen, and also pure hydrogen or mixtures of these two. Again, we'll have 4 speakers coming from various sectors, academia, industry, and coming from around the world as well. So I'd like to welcome immediately our first speaker, Dr. Jamie Larfeldt. Many of us know her well in the combustion community, seen her speak many times about innovative gas turbine technologies being developed in the industry. She is an adjunct professor at Chalmers University, where she also received her PhD in almost 20 years ago, year 2000. And she has been working in Siemens Energy in Sweden since 2004. And one of the world-renowned experts, industrial experts, in terms of gas turbine combustion, design of new systems, low carbon fuels, and different types of industrial turbine systems. And today she's going to talk about, and I'm sure we're all going to be very interested to hear, innovations in ammonia hydrogen gas turbine. Hi, Jenny.
So, hi, thank you very much. I share my screen. So here we go. So carbon-free fuels. I immediately start out with how far we have come with our hydrogen capability of the medium-sized gas turbine frames that we work with here in Finspång in Sweden. And as you see, for the SGT 6, 7, and 800, we have now released for sales with up to 75% by volume hydrogen in mixture with natural gas. So this means 75% by volume means that half the energy content in the fuel is carbon free, meaning that we reduce the carbon footprint by half. So we still have a way to go to continue our development. I also show our younger turbine, SGT 750, that is currently offered with up to 40% hydrogen. But we will start out activities also so that this will come into parallel to the other frames. We have worked with hydrogen on our dry low emission systems, the 3rd generation DLE systems, since 2008. Before 2008, we have experience of hydrogen firing at very high level in conventional diffusion burners. So from the 1980s, we have experience on from the auxiliary point of view and from these combustors. But in 2008, it started out with a high pressure single burner combustion test at our sister site in Lincoln, UK. And from that on, we performed tests in 2012 and 2014. We were feeding 1 single burner in a full engine in our test bed, where we also do delivery tests of gas turbines to our customers. One enabler for this development is additive manufacturing, and this is the way we have been working with adapting our burner design to more reactive fuels such as hydrogen. So we are 3D printing the burners, and on the lower part of the picture you could see 8 burners. We used this very same burner in both the 6, 7 and 800 gas turbines. They have annular combustors, and we used this very same burner in all 3 of these frames. Here you can see a building plate straight out from the printing machine. It's 8 burners in one building plate. And the next step is to cut them off the building plate and weld on a shaft on these burners. We opened this workshop in 2016, more than doubling our capacity of printing at that time, and we have increased. Yep. Sorry,
Jenny. I think we actually think it's frozen. It seems to be stuck on slide 3, and your video is frozen as well. Can you maybe stop sharing and share again?
Maybe I should do without the video.
Okay.
If the net is, yeah, it says host has asked to share your video. Okay. This.
I think you were yeah. We're seeing the slide 3 still.
With the timeline.
Yes.
I'm still on this slide actually.
Apologies. Okay. So it's just the video.
You think I'm talking too slow? Here we go. No, Can you see me now?
It's okay then. Everything is working fine.
Yeah. Good. It's so terrible these times, and I'm so sorry I can't be with you in real life. No, and we started out additive manufacturing in 2016, and in 2017 we did a full engine test on the STT 800 with up to 50 volume% hydrogen. And we kept developing, and I will come back to on the next slide on the test we did on the STT 600. And so I think I can go there immediately. This is from a publication at the ASME last year in London, or it was virtual, but we did test our smallest frame, STT 600, 24 megawatt electric, with over 60% in hydrogen in natural gas. And this picture shows a test we have done at our high pressure test facility in Clean Energy Center in Berlin. Here we test one burner, but we test it at the full pressure and temperature it would experience in the real gas turbine. Here you can see the purple line indicates the hydrogen content in the mixture. So you see at 20 past 1 o'clock on the x-axis, we have 50% by volume hydrogen. And then we increase it up to 80, 90, and then we run 100% hydrogen. This is something that is easily done at such a test center. And this test was performed in 2019. So we were very confident that the burner works, and it's able to run on 100% hydrogen at corresponding full engine conditions. Or you could see in numbers here the corresponding load estimated on an STT 700. So this was 90% load. This is full load conditions. Full load at 100% and then 95% load about. And you could see the NOx emissions from 25 ppm NOx increasing as we go higher in hydrogen content. And here we are about 40, 50 ppm NOx. And this is something we target in our development too, to understand how we could also tune the burners to lower the NOx emissions. Let me see. The red line corresponds to a measured wall temperature in the high pressure liner in the rig. And it's divided by 10. So you could see we are between 1100 and 1200 degrees Celsius temperature on the wall. And as you can see, since we have dry low emission burner, we keep the flame temperature, although we change the fuel, and there is no impact on the wall temperature. You could see in the pictures, photographs, that as long as we have natural gas in the mixture, you still see this kind of bluish shape of the flame. But as we turn into 100% hydrogen, the flame becomes invisible. The outlet of the burner is more or less a black hole, and you see the hotspot or the heat load on the ceramically coated combustor wall. We also tested in the real engine, and for the SGT600, we can offer on high hydrogen. We have a combustor that's annular, and this is a cut through this combustor. It's film cooled, as you can see here. And we have our burner, 3rd generation DLE, and for both the SGT6 and 700, we have a combustion bypass system, meaning that air can be directed to bypass the combustor and then entered towards the rear part of the combustion chamber just before entering the turbine. And this has been a very useful way to also have good performance, low emissions, also at part load operation for these turbines. Here I show the combustion dynamics frequency spectrum for operation at full load and with minimum pilot with the hydrogen adapted burner. So this is normalized frequency, and operating on natural gas, we could see we have a peak in some dynamics in around 70, 73 here with an amplitude. But the minute we add hydrogen, and this is hydrogen content above 40% by volume, this vanishes. So our experience is that hydrogen stabilizes the situation in a sense. These tests and we did for a customer, Braskem in Brazil. So this is just a page showing, unfortunately due to COVID, these 2 frames have not been commissioned yet. But there are 2 units that will run on power generation with up to 60% hydrogen in the process gas that the customer Braskem have in their industrial process. So this is a picture from site, and hopefully they will be starting commercial operation this summer, maybe as we speak. So that will become our fleet leaders on high hydrogen with DLE combustion system. We have worked, and maybe you are already aware of, but this is a collaboration with combustion physics at Lund University. In the picture is Arman Subash, who at the time did his PhD work looking into our combustion rig with laser equipment. So in the rear part of the room, you could see our atmospheric combustion rig. And in the front, you see all the laser equipment that Arman brought with him from the university. And it's by far bigger than our combustion rig. In the combustion rig, we mount a real burner that potentially have been running in the gas turbine. So it's the real size, but we run at atmospheric conditions. So it's 20 times lower power density. In this measurement campaign that was published, referenced on the previous page, Arman and his colleagues took a high-speed camera imaging from a laser sheet just in front of the nose or the tip of our burner. And you get this very kind of nice images where you see really the details in the turbulence and the flame front. It's OH radicals that you see, and you see the movement of the flame that it sometimes appear in the picture and then sometimes it goes outside, moves forward. So there is an axial movement of the flame captured really nicely. And if you look into this paper, you could also see a comparison operating in the lower picture on natural gas, where you see that some pictures in the mid of the sequence is pretty dark. The flame has moved out of the picture. While for the hydrogen, the upper pictures, you see that the flame tends to move closer to the burner exit and it tends to stay there. So it's kind of stabilized there. And you can see this really, you can imagine almost this swirling motion that the flame has. So really nice, beautiful pictures. And for us, very important to have this more fundamental understanding of what changes in the flame as we turn into more and more hydrogen. We have also, my colleague Daniel Moel has made an industrial PhD on numerical modeling of hydrogen enriched flames. And I only took this figure from his PhD thesis, where he is comparing. This picture again shows our atmospheric combustion rig. And here is a position where we have a pressure transducer. So we measure the dynamic pressure inside the combustion chamber. And then Daniel did CFD modeling. And he compared LAS models with SAS models, the red and the green lines with the measured data from the combustion rig. So all of this again is atmospheric conditions. But this kind of comparison is also giving us a lot of fundamental understanding and confidence to go up on the real engine level and to continue our work. When it comes to ammonia, we have been collaborating with NTNU and SINTEF in Trondheim, a very extremely useful collaboration and a lot of fundamental understanding we have gained in the last 3 years. In this work, we have focused more on our STT750 gas turbine, which has what we call the 4th generation DLE combustion system. Obviously, since the other one was the 3rd generation. But DLE is the standard also for this frame. And this is a cut-up of the real combustor can. It's 8 combustor cans, and we have the burner or the top hat in each can. We have supplied for Trondheim University a small-scale burner looking like this in the sketch. So it's a central pilot body, and we call it rich pilot lean. And then there is surrounded by a stronger pilot. And then we have the main flame entering radial into this conical shape of this burner. So it's a radial swirl burner. And for this lab scale size one, the main swirler is much smaller than on the real frame. As you see here, we have a double core cone, and we have addition of main fuel in these positions. So of course this has a much less thermal power than the real burner. But this also makes it possible to run this kind of nice flames in the laboratory. And this was made by Samuel Weisman, working with James Dawson and Nick at NTNU. This is an ammonia flame, and it's very apparent that you get this kind of orange color of these ammonia flames. Sam is working on a publication, and he has been studying the influence from fuel splits and ammonia decomposition ratio on thermoacoustics and emissions of nitrogen oxides. So this collaboration is performed in a project called Big H2, enabling safe, clean, and efficient utilization of hydrogen and ammonia as the carbon-free fuels of the future. It's funded by Gassnova in Norway, and partners are SINTEF and NTNU, but also Equinor and us in Siemens. So this is just a sketch illustrating the beneficial of ammonia storage compared to hydrogen. And then what we have been looking into, the cracking, the amount of cracking needed. And initially we were looking for a mixture of ammonia, hydrogen, and nitrogen that, if it was possible, could resemble natural gas in its combustion characteristics. Of course, with having in mind that we should stay close to our existing combustor designs, but I'm not sure it's really that easy. SINTEF has also looked into pressurized tests. This is from a rig, Hiprox rig, and this work is funded by the Research Council of Norway and performed within the Low Emission Center. It's a center of very many oil and gas industry partners collaboration, and this low emission aims to develop technologies and solutions needed to reduce offshore greenhouse gas emissions on the Norwegian continental shelf by 50% within 2030. And there is also a publication presented very recently at the ASME conference in Pittsburgh, where you could look into more details from the testing that Mario Di Taranto and Inge Sanum performed in this slightly high pressure rig with various splitting ratio. So to the left, you see a flame consisting only of hydrogen-nitrogen mixture, and then towards the right-hand side is 100% pure ammonia flame, and in the middle it's mixtures of decomposed ammonia and pure ammonia. There is also work performed at Lund University that is supporting our understanding of ammonia, and this is a slide made by, or a figure I got from Alexander Konov, and working with colleagues on the fundamental laminar flame speed. The dots are measurements, and the solid lines are from different kinetic mechanisms. And it seems to indicate that there are room to understand more about ammonia combustion for different stoichiometries, and also for us to understand when we should control the NOx formation from such flames. And this work has been made within the frame of Center of Combustion Science and Technology at Lund University Combustion Physics. Also modeling and measurements have been performed. So there is a PhD thesis coming up in October 21. One of Shusong Bai's students will graduate. And there is also experimental work reported where they have, from a burner design, they have been able to capture not only OH radicals, but here also NH radicals. So this work is very encouraging and will also support us. But if I boil down the question to, so can ammonia be used in Siemens industrial gas turbines? my belief is that we need to continue this kind of fundamental work on how far we will get with our existing combustion systems and what is needed beyond. It's interesting to continue looking into decomposition of ammonia, and especially how decomposition could be made on a whole power plant perspective. And the other way would be to live with the NOx formed, but to look into the potential to scale up the secondary nitrogen oxygen abatement. And here I'm not an expert, but it would be interesting to learn from all of the other presenters today and other experts. And then we also feel very strongly that we need more input from the market, how ammonia can come into play. Is it only for storage, or will it be mainly for offshore use? And is there also an interest to co-fire ammonia with natural gas? So we feel that there are some questions still to be understood, and we are working on it currently. So in my last slide is a bit different topic, but in Finspång we have now built a demonstration plant we called Zero Emissions Hydrogen Turbine Center. And it's an ERANET project with funding from the EU. And it's made with university partners, Chalmers in Gothenburg and University de Bologna in Italy. It's also the Finspång municipality and the regional board, as well as the gas supplier, our gas supplier Linde Group is partner in this project. And there is an animated movie one can see at this address, but basically we are making use of excess power that we produce when we test our gas turbines for customer. And with this excess power, we use it in an electrolyzer to produce hydrogen that we store. And this hydrogen we then can feed into the natural gas we use when we test run our gas turbines, so thereby reducing our carbon footprint. Since we test run gas turbines not every day and for a shorter time during a day, we also installed solar panels to be able to produce hydrogen in a more continuous manner. So you are very welcome to read more about it, and we are happy to invite you to Sweden when everyone is allowed to travel again, to come out in the forest and see this demonstration plant. So thank you very much for your attention.
Okay, thank you very much, Jenny. I definitely want to come to Sweden now. It looks like you have sunshine outside, which is a good time of year.
Yes.
Okay, so we're going to keep the questions to the panel discussion, and we're going to go through the remaining presentations. So our second speaker is Professor Valera Medina from the Cardiff University School of Engineering. And Professor Valera Medina, he's one of the preeminent experts in ammonia for power. Many of you might know his very famous PEX article, Progress in Energy Combustion Science, about ammonia for power. He's written books about it. I think I was surprised to see that over a quarter of his PhD students have done their thesis on ammonia, and almost a third of his papers are about ammonia. So definitely one of the world leaders in this area. He got his bachelor's degree from UNAM in Mexico. We have a lot of students in KAUST from Mexico. You can appreciate that one of the experts in ammonia comes from Mexico. And then he got his PhD in energy from Cardiff University. And I'm sure we're going to learn a lot about ammonia, hydrogen combustion, and gas turbines, as Professor Valera Medina has a lot of industrial experience with most of the major gas turbine manufacturers, automotive companies, aircraft companies as well, in terms of developing these systems. Are you okay to share?
Absolutely. Thank you very much, Manny, for that lovely introduction. And yeah, let me share my screen to then show you what we're going to be talking about. And again, thanks for the invitation. It's great to be here with you. And hopefully next time it will be just face-to-face. So I'll be talking about ammonia blends for gas turbines. The subject, just as mentioned, is vast, is lovely, is exciting, and I think it's going to then make a difference in the near future. So I'll just go through all these points and introduction, changes, challenges and developments, some collaborations that we got ongoing, and then some final conclusions. It's something that is interesting because when we talk about these renewable energies, we know that they're going to be needed for reducing greenhouse gases. At the same time, we know that they have loss of intermittency, which is a main problem, especially when it comes to the countries that are now relying on it. And we have cases where this lack of sustainability or reliability has impacts, and that we have seen it already. Here in the UK, we lost power in almost 1 million houses one day when they were running at 50% wind power, and something similar happened in Australia with a 2 weeks blackout years ago. So therefore, we need some way of then storing all this energy, and then one of the ways is obviously using chemical storage. Here you can see in my slide how a comparison from the Hydrogen Council was looking into how we can then store some of this energy. And obviously we have all these renewables, then comparison with natural gas sources, and looking into the hydrogen bit is really interesting how they approach it. So they see ammonia as one of the vectors that can be used for hydrogen storage, another one liquid hydrogen obviously, and then the other one, the liquid organic hydrogen compounds that we got. And they just present 3 different scenarios, and you can see really interesting that the one that presents a really nice cost for the movement of the hydrogen is obviously ammonia. And if you see what is the main factor is actually increasing, that is the cracking of the molecule. So if you just get rid of the cracking that you got from the production, then transportation from Chile to the US of almost 0.9, 1.8 US dollars, that would be the most cost-effective method of moving the hydrogen, if we were going to then have technologies or a mean to then reduce that cracking process. So that being the case, obviously, I'm thinking that hydrogen still is a problem in terms of stability, just as mentioned in the previous presentation. It's like loses the combustion, we stop seeing it, and therefore it's more dangerous to then handle and more difficult. Again, it's been possible, but there are some other options, as I've shown here with ammonia. So that's the reason, because it's becoming now an interesting subject in terms of power distribution, energy generation. We can obtain it from renewable sources. We can then obtain it from stranded resources, waste streams. It has the potential of then reducing the amount of money that we're paying for then distribution and storage of to 30%, 30 times more than hydrogen. We can then use it in isolated locations or islands. It's a fuel, but also obviously has been used for almost 200 years as a fertilizer, has a very high hydrogen content, interestingly, because we have NH3, 3 atoms of hydrogen. It has more hydrogen than hydrogen itself in its liquid form. And also there's a massive market for it as being the second largest distributed chemical worldwide. If you compare the hydrogen density materials and carriers that are available in the market, ammonia again becomes as one of the top, and therefore the interesting bits of using it for power generation. The idea comes from then having all these different methods of then recovering the energy, or even using what is called blue hydrogen by carbon capture and storage, and therefore using this to then produce the ammonia, where we need it to then distribute it a very long distance or store it for long periods of time. So if we do that, we can have then the options to then either crack it, as you have seen in the previous slide, ship it or distribute it over long distances, and then use it for transport, heating, cooling, process industry, propulsion, stationary power, etc. But there are many questions yet that need to be answered, and those are related to the reaction and combustion, public perception, regulations, economics, and environment, things that need to be solved before we get into demonstrating that actually ammonia is a feasible chemical. Now, interesting, and things probably for those that have been working on this field for now more than 5 years. I've been working on it 6 years, and I'm pretty sure some of my colleagues, they have worked a little bit further, especially in Japan. We used to hear a few years ago that this was just a dream, it was never going to be possible, and why would we want to then burn ammonia? People honestly they would laugh at us in some meetings. And I remember that from my boss that used to say that it was a fairy tale. Now you can see the big, large-scale programs that are worldwide talking about ammonia. We're talking about 5 billion renewable in Saudi Arabia, the distribution of energy from Australia in gigawatts power, 30, 40 gigawatts power that will just be expected by 2035, and the massive plans of now ammonia plants trying to convert to renewable energy. So those kind of things have been the effort of the work that colleagues, especially in Japan, they have put together and then managed to then get going. But there are still challenges, and there are things that need to be solved. First of all, we need to then produce it in a lower cost, higher efficiencies. We need to produce at a utility scale and demonstrate that it's feasible, stable, and that can produce low emissions. Public acceptance as well needs to be proved, because otherwise, if the public doesn't want it, we won't have it there, and then the economics need to be profitable. Here, in the case of gas turbines, I present you this interesting slide that I got from some of my colleagues in Oxford, and they do lots of techno-economic analysis. And just to compare what would be the case of having ammonia and hydrogen, and this is one of the things that, again, we want to prove to those running these units, is ammonia, again, a feasible vector. So if you were thinking about using SGT 800 or 900 HL units, one at 80 megawatts power or 850 megawatts power, and you were thinking about then use or produce that energy via hydrogen, what you would require would be either just to run it 1 hour, 8 tube trailer containers of half a ton of hydrogen. If you were thinking about using that unit for 1 day, you would need 8 kilometers of 1.4 meters diameter pipeline. If you were thinking about using it for 1 week, then you would need 3 NASA tanks for the shuttle to then run it for that time. And then if you were thinking about then having an SGT 800 for a month, you will require 4 T-side sea salts of 810 tons, each of them, to then power these units. And it gets worse as we go to 870 megawatts. We're talking about almost 2,500 kilometers of pipeline just to run it for a month. What would be the scenario if we were thinking about using it with ammonia? The scenario would be really interesting, because using just 2 anhydrous ammonia tanks that are very common and very commercialized in industry, they've been around for decades, you could then run these units for 3 months or 1 week. Again, this is what could make the economics, and everything just goes back to the way that we're liquefying, converting the chemical, and then using it, and its density and the amount of hydrogen that it's got by itself. Thinking about, shall we go for just cracking or just the pure ammonia? Well, there are many things, and they relate to the efficiency and final combustion that we'll be talking about, and you'll be seeing over the session today. And some of these thoughts were thinking, okay, we need to then go through different phases. Phase 1, we've been talking about hydrogen units that are almost commercial or commercialized already in many places. And if we think about having the ammonia crack completely and then producing this hydrogen nitrogen stream, then the efficiencies are being calculated around 52%. When we think about phase 2, where we then increase the amount of hydrogen in ammonia blends, we don't crack it entirely, but we just boost some of this combustion, then potentially we can reach around 56, 57%. And if we think about using ammonia purely, then the efficiencies go about 60%. Now, here comes the trick. And the thing is that running 100% ammonia is obviously more difficult in terms of combustion and emissions performance than if you were running with some other blends. So that's one of the things that we've been doing here in Cardiff. We've been working and then trying to understand fully what is going on and what happens when you try to run with pure ammonia blended with hydrogen, with methane, with coke gas, with syngases, etc., to then determine what are those parameters of stability, what are the best methods of injection that you can approach, and therefore try to then go for a technology that is going to allow us to then reduce emissions while enabling stable combustion. We, as our colleagues in KAUST and in Japan, have addressed that one of the potential possibilities of doing this is going with secondary stationary combustion, where you run in rich conditions in the first stage, and that way you use the same ammonia to reduce the NOxes that are being produced in that region. And then once that you have produced enough hydrogen, which is one of the trails that you get through this concept, you can then post-combusted in a secondary stage part of the combustor. And that way you reduce the emissions and they can then go down very low in terms of NOxes and remaining on-board ammonia. Some other ideas are as well using different premix or diffusive injection methods that as well will impact on the NOx emissions and the onboard ammonia that you got, the hydrogen that can be produced. We have looked into the operability of these methods as well, following some of the trends that now KAUST has been putting together in terms of some of the research that they've been developing. Emissions for NOx, ammonia, hydrogen, nitrogen, etc., and modeling techniques that we're now exploring with some colleagues in different parts of the world. For our development plans, what we have is a really interesting program called SAFE. And in this program, what we are attempting is to then create a new combustor. As mentioned before, now 3D printing is the way forward. So we're 3D printing new ideas, double checking CFD modeling via advanced modeling techniques, and also retrofitting auxiliary power units to then assess some of these concepts. Similarly, in our facilities, what we're doing is at higher pressure, different blends. We're attempting these RQL rich quench technologies to then evaluate what is the potential of reducing emissions while keeping stability. And all those thoughts and all those ideas will be assessed in an SGT 400 unit in collaboration with Siemens Lincolnshire. That is part of our consortium in this program. Also, another bit that we're looking at is the design of new cycles, cycles that will improve the efficiency that I've been talking about, and that are reaching now concepts of around 60% efficiency when we even split some of this hydrogen at 30% and then keep the combustion stability. We're also doing life cycle analysis where we're just finding that it will be obviously different bringing ammonia from Chile, Morocco, or Australia here to the UK or Europe, which is something that is well we're trying to attempt. Just to then wrap up some of the ideas and things that are moving forward, probably all of you know that there are now calls, as someone communicates from Mitsubishi, that they're saying that by 2023, 2024, they will be running the first gas turbine purely on ammonia, 40 megawatts power to demonstrate. On that thought, we have then gone through very fundamental research and passing through all these different aspects, and now we're at the stage of implementing everything in an APU, and then the concepts and things that we gain from that experiment with that research will then implement it in SGT 400, SGT 500 units in Siemens Lincolnshire for a larger power. Similarly, we are working with some European partners. Now we're just putting together ideas for a plant in Portugal, in DDP, and the concept goes as recovering energy, then transforming into ammonia, and then using it in power plants for production of peak power. Here are some of the programs that we got. We go from early demonstrationable and commercial systems, and in areas that conclude chemical, natural, renewable, and business ideas that will then include internal combustion engines, marine, aerospace, etc. We got lots of different topics going on with this exciting field. These are some of our collaborations. We got colleagues everywhere, KAUST, and Tohoku, Orleans, AIST, etc. You name it, is just been fantastic, and it's a lovely subject. If you haven't jumped into it, it's something that I recommend you to do, because now the momentum is there. Just to conclude, ammonia is a really interesting chemical to decarbonize cooling, heat, power, and propulsion generation. It will then allow us, if we do it properly, reduce NOxes and onboard ammonia. This is what we are doing now in combustion systems. Research is ongoing in all these different aspects, and now people from social sciences, bios, laws, etc., are jumping in, because we need regulations. We will need to understand fully what is going on in terms of environment, and then we can have, through all this collaboration, a hydrogen through ammonia economy if we work it properly. Thank you very much, and any questions, please just drop them in the box.
Thank you very much. I think there's already some questions coming into the Q&A, so keep them coming. Again, we'll answer them all at the same time at the end. And again, I think some of the questions as we watch the presentations are also being answered. So thank you very much, Professor Valera Medina. Very nice talk. And now we will move to an internal speaker, okay? Dr. Thibaut Giberti. He's been at KAUST for about 6 years, I believe. working as a research scientist or a senior research scientist in the area of combustion, experimental combustion, and more recently spearheading and leading most of the work here at KAUST on experimental combustion using ammonia hydrogen mixtures. So Thibault has his PhD from France, from Paris-Saclay, and also his habilitation, which is like a 10-year track professor position there at Toulouse. So I'm sure he's going to talk more about the work we're doing at KAUST, and also will be interesting to our international speakers and guests. Thank you, Thibault.
Great. Thank you, Manny. Right. Hi, everyone. I'd like to first thank Bassam and Gaetano for the opportunity to show you some of the work we are doing here at KAUST on ammonia hydrogen combustion, always with practical condition in mind. So what I'm going to show you today is the result of a few years of work. And so, of course, this involved a number of people, including people who actually graduated now from their PhD, and all of this under the supervision of Professor William Roberts. And what I'm going to show actually is funded by one of our partners, Saudi Aramco. So given that this is the third presentation in this session, I figured that there would be no need to further introduce why hydrogen ammonia combustion is relevant. So I go straight right in. And so basically, to summarize the discussion we've had with Aramco a few years back, they were telling us, okay, we'll buy you this micro gas turbine, just decarbonize it. So we said, of course, thank you very much, we'll do it. And so the gas turbine that was selected was this one, so Ansaldo T100, which is originally designed for natural gas, 330 kilowatt thermal for 100 kilowatt electric. So there are different ways you can go at this problem. One is to say, okay, we'll keep the same hardware and we'll shoot for partial decarbonization. So we'll continue using natural gas, but we'll replace some of it progressively with either ammonia or hydrogen. So obviously we know that there's a limit to this. If we put too much hydrogen, probably we'll have flashback issues. And at the opposite, if we put too much ammonia, we might have blow-off issues or NOx issues. At the other end of the spectrum, we can say, okay, let's potentially redesign totally the combustor, which is fairly easy to do with this unit, and shoot for total decarbonization. And then we'll be using either pure ammonia or pure hydrogens or blends of the two. But there is a third way, where we'll still be shooting for total decarbonization, but still keeping the same hardware. And it's actually very useful short-term or mid-term for the industry. And this time, we will basically be using blends of ammonia and hydrogen, because we know hydrogen is much more reactive than methane or natural gas. Ammonia is much less reactive. So I guess by blending the two, we have a chance to be able to tailor the proportions to the reactivity of the natural gas. And then we can use the same hardware. So here at KAUST, we are working on these three strategies, but today I'll talk specifically about this one with fuel blend tailoring. So obviously, doing it directly in the gas turbine is challenging because we don't have optical access and any mistake can be very expensive. So we started at low scale, small scale, lab scale, at atmospheric pressure, but with burners with good optical access. So we're talking a few kilowatts. Then we graduated from this and we went in our high pressure combustion facilities when we can mimic the pressure of the gas turbine, which is actually 5 bar, around 5 bar, but we still have optical access. And so we're talking 25 kilowatts. And of course, going in the end for the actual gas turbine. And so this is essentially the outline of my presentation today. So starting with this atmospheric swirl flames. So we've used a generic lab scale swirl burner, which is used to stabilize technically premixed ammonia hydrogen air flames. So you have a schematic here on the right. So it's very generic, right? And so we induce the swirl by a mixture of actual and azimuthal injection. And so we varied different parameters, including obviously the ammonia volume fraction in the fuel blend from 0 pure hydrogen to 1 pure ammonia. We also varied equivalence ratio from lean to rich. We played with Reynolds number, swirl number as well. And so what I hope you're able to see here at the bottom are different examples of these flames. So these are direct pictures with DSLR camera, so true colors. Here, this is almost pure hydrogen, and on the other end, it's pure ammonia. And so we see that all of these flames, they are very typical of what you'll find in a single stage gas turbine. They are V-shaped, And so the size is roughly the same regardless of the fuel blend, but of course the coloration changes a lot. So these are just examples, but we've mapped all of these conditions that we talked about to try and understand the stability limits for this burner. So we've measured the stability limits, which I plot here as a function of equivalence ratio and ammonia fuel fraction. And so essentially what we see is in light gray, we have the flammable zone. So this is the region where at least we have a chance to ignite. Doesn't mean the flame will be stable. And in dark gray here, we have the region which we find was providing stable flames. And this is bounded by different limits: flashback, lean blowout, or rich blowout. And so as we progressively enrich, or I guess the opposite of enriching with ammonia, we see that the stability limits, they are modified. Actually, with this burner, that's very burner specific, but the stability limits are widened when we put some ammonia. And interestingly, we see that at around 70% ammonia in the fuel blend, we have this very sudden transition where we don't observe flashback anymore, and this transition goes to rich blowout. And essentially, this means that if you put enough ammonia in the fuel blend, the reactivity goes down, and even a very fast stoichiometric mixture is not fast enough to flashback, and so you lose the flame only with rich blowout. So essentially, we're able to stabilize with this burner a large range of different fuel blends. And just for reference, I've put in here the stable range for methane air for the same burner. And consistent with the literature, we find that we have a similar stability compared to methane if we use around 70% of ammonia by volume in an ammonia-hydrogen blend. I just don't want you to think that there is something special about 70% ammonia in the blend in terms of chemistry, right? Actually, there's nothing special. We tried these stability limits for different Reynolds numbers, and we find a different critical ammonia fraction for this transition. So this is not chemistry, that's aerodynamics. And also something important, so far we've done only for this plot hydrogen ammonia, but it's actually very unlikely that we would be using hydrogen ammonia mixture in a gas turbine, because this hydrogen would be coming from ammonia, which we would partially crack, and so we would be creating also nitrogen. So in fact, we would be working with ammonia, hydrogen, nitrogen mixtures with a 3:1 hydrogen-nitrogen ratio. And so we repeated the stability limits, and the dashed lines here are showing the ones with some nitrogen, and they're marginally modified. So what we've learned so far will still apply, even if we put this small amount of nitrogen in the mixture. So it's all well, we can stabilize many flames, but this is useless if the flames have punitive emissions, especially NOx emissions. So we've measured as well the NO emissions in the exhaust of our flames. And so this is what I'm showing here. So NO in thousands of ppm, so 1 stands for 1,000, as a function of equivalence ratio for different ammonia fractions. And so we can focus first on the one for pure ammonia, which are the squares here. And so what we see is that if you are close to stoichiometric and lean, you have massive amounts of NO in the exhaust. We're talking many hundreds, sometimes thousands. So of course we can't use these flames. But we find that if it is slightly rich, then we have good NO performance. So we're not the only one who found this in the literature. And actually, people have seen this also consistently with ammonia, methane flames. And so this is important because if you choose to burn here your flame, then you have some unburned ammonia, which you eventually want to burn. So this forces you to have a second stage of combustion, so that you make sure that you have a globally lean operation, even if the first stage is locally rich. So what's interesting now is that if we start to put some hydrogen in there, because hydrogen is more reactive than methane, we actually are able to go to leaner flame that will not be possible with methane. And we see that if we are lean enough, then we start also to recover a very good NO performance. So this is potentially promising for future application because this will not require a second stage. But we have to be mindful that for this condition, we might have other kinds of emissions, which we will need to consider as well, specifically N2O. So rather than talking about N2O right now, I'll talk about elevated pressure. So far the experiments that were at atmospheric pressure, but of course the gas turbine will operate at elevated pressure, around 5 bar. So we've put our burner in the high pressure combustion duct, which we have available here at KAUST as well. And so these are examples of flames which we took in the HPCD. So these are all for stoichiometric pure ammonia flames. So the same flame, essentially the only thing that's changing is pressure. And so the shape of the flame, the size of the flame, the color of the flame is the same. The only difference is that as we increase pressure, we increase thermal power, we increase Reynolds number linearly, and so the thickness of the flame brush increases. So that's why the flame look more blurry. But these are essentially the same flames. So we've repeated these stability limits, which I show you on the right, except this is in 3 graphs for clarity. So this is rich blowout, flashback, and lean blowout. And so what we see essentially is that all the points that are on top of each other almost. So pressure barely modifies stability limits. And if we were picky, we will be able to see that actually pressure promotes flashback and retards blowout, which essentially means that as you increase pressure, you boost the turbulent burning velocity. But regardless, we see that we are still able to stabilize these flames at elevated pressure. Right, so we also did emissions at elevated pressure, which is what I'm showing here. So the plot on the left focuses on the sufficiently lean flames, and on the right, the sufficiently rich. Although, keep in mind that this is for ammonia methane. I was not able to find, when I prepared this, the plot we have for hydrogen, but I know that the trends and actually the numbers, they are very similar for hydrogen anyway. And so we see that even at pressure, we are able to find a mixture that is sufficiently lean or sufficiently rich to achieve good NO performance. And in fact, what we see is that the higher the pressure, the lower the NO. So increasing the pressure helps us to achieve good NO performance. So what about N2O? So we know from literature that if it's too lean, the N2O emission can shoot up. And this is because the N2O that is produced in the flame is usually thermally degraded in the post-flame. But if it's too lean, it's too cold, and you don't degrade it. And that's potentially problematic because N2O is a very potent greenhouse gas. So if you have too much of it in the exhaust, you're kind of destroying the benefit of not having CO2 in the exhaust, right? Because you still have a huge greenhouse impact. So you don't want that, obviously. So we haven't measured N2O yet because the machine was not available at the time, but we are doing it right now in the lab, except Christian is here. So I guess we are not currently doing it right now, but later today. And so this is the expected trend of N2O. So if it's quantitatively like this, we're in trouble because you can't find any equivalence ratio where you have low NO at the same time as low N2O, right? But maybe the curve is like this, right? We'll learn soon. And so if you're like this, then there is a sweet spot here where you have low NO, low N2O. And so that's what we are hoping. So we've done something else also. So far, the burner was very generic. It doesn't look like an actual gas turbine burner. So what we've done also is that we've created a replica of the Ansaldo gas turbine burner, albeit at a much smaller scale so that it fits in the HPCD. And so this is the burner that you see here in photograph and here in 3D. And so although all the dimensions, they are different from the gas turbine, all the features, they are the same, right? We use a pilot flame and a main flame and very similar swirl and injection strategies. So hopefully we can learn a lot with this burner because it will be operating with the same blends and at the same pressure, and we can then scale it up. And so to make sure that what we learn will apply with the full-scale burner, we've actually conducted simulations to make sure that the flow field, the recirculation structure, and also the main features of the flame, they would match. And so this is what I hope you are able to see here. We were able to be convinced that the scaling down was working. So we've put this burner into the HPCD and we've done some stability limits. And so we found that they're consistent with the generic burner. We did not notice anything special, except that because we have this pilot now, we are able to push the flame to even leaner, which is what you see here, leaner, 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 leaner. But in fact, even though the flame is still there, at some point it's so lean that only the pilot stays and the main flame is dead. So it's not useful because you're wasting most of your fuel. But so we are able to stabilize all of these flames, and we will be measuring also the NOx emission in these flames. So, as I said, there are two options, whether we find a sweet spot with low N2O, low NO, or we don't. We'll know soon. But so if we don't find it, then we will have to resort to this locally rich burning and then this second stage of combustion, as Professor Valera Medina mentioned. And so we also verified that this burner could be used as the first rich stage. And so these are pictures we took with 1.2 equivalence ratio, where we see that the flames are stable for different ammonia fractions. And quickly to finish, so once we identify these promising operating conditions, we will work with our gas turbine. So these are pictures of our gas turbine, which is currently in the lab, which will be commissioned, actually ignited for the first time with natural gas next week. And so we are targeting 330 kilowatt thermal power, 30% efficiency without any carbon. So my conclusion, so over the last few years, we've been studying ammonia hydrogen source flames with different burners, different scales, different pressures. So consistent with finding from many other groups, we found that local ridge burning is a viable solution, but you need a second stage. And hopefully we can find solutions for this lean only single stage. And with that, I thank you for your attention, and I will take your questions at the end of the talk.
So we'll move to the last presentation from Professor Christine Mounin-Roussel, a very well recognized and renowned professor from the University of Orléans in France. She has led one of the preeminent combustion groups there, combustion engine groups, the Prisma Lab, which is well known for a lot of work on HCCI engines, biofuel combustion, optical diagnostics. And more recently, she's been advising also the IEA on sustainable mobility, clean and efficient combustion, as well as the Institute for Energy and Petroleum in France. Christine today is going to talk now, shifting away from gas turbine and looking at ammonia use in internal combustion engines. We can see your screen, Christine. Please go ahead when you're free.
Yes, thank you, Manny, for this nice introduction. I hope that you hear me, everybody. So yes, I will focus more my talk about the potentiality to use ammonia as fuel for internal combustion engine. So first, there is some problem. Wait, always I have some problem. I don't know, I cannot, it's okay. So in fact, yes, in fact, if we look at the history of ammonia as fuel, it's a brief history about 80 years. And it was first during the Second War, when there was a mix of ammonia with syngas, coal gas, was used to fill, in fact, buses. 20 years after, US were also interesting about the use of ammonia and try to consider it, but with a lot of paper about fundamental issue to use ammonia as fuel and not some real realization. We have to wait until 2010 around to have a new interest about using ammonia as fuel for internal combustion engine, first from Michigan University, when they mixed ammonia with gasoline, and also from Korea to use ammonia with gasoline until 70% of ammonia in the fuel. And also there is I'm using also another interest from Japanese, from Toyota. We are still interested, in fact, in use ammonia as fuel for internal combustion engine, but we can see for all these cases, in fact, always it's mixed with usual fuel for combustion engine. And new projects are more focused on the use on ammonia as fuel, but also with the help of hydrogen. So, in fact, okay, I have some problems. Oh, it's okay. If we look a little bit more in detail, this is for spark ignition application. In fact, before 2012, 2013, most of the cities are more focused on CFR engine, so not all engine. And after, we can see that you have some experiment done in a multi-cylinder with different size of engine and also different type of compression ratio, but as it is for spark ignition engine, the compression ratio is relatively low. The higher is 10.5. It is interesting also to see that, in fact, there are different ways to consider ammonia as fuel. For example, for Britain University, the objective was to use it for range extender. So in fact, the engine was very small. Texas University tried to improve the use of ammonia with a mix of ethanol and gasoline due to its own properties. And more recently, in fact, in Korea or also in they want to use ammonia thanks to the use of thermal reformer, especially to improve, in fact, the problem at the cold start. If we look at the same thing but compression engine, what we can say, in fact, there is not so many, in fact, experiment to use ammonia in compression engine. On most of the case, it's a dual fuel. So with the help of diesel spray, we can see also that we have the first study in University of Holland with University of Leuven. It was focused on HCCI with ammonia. And recently there is, in fact, an improvement on the combustion for compression engine with a John Deere engine with a high compression ratio. And also it's similar to what do, in fact, actually Toyota. It's with a thermal chemical treatment of ammonia in order to seed, in fact, then directly hydrogen in the engine. So, in fact, if we consider that we can use ammonia in both spark ignition engine and compression ignition engine, as function of the way we can mix with hydrocarbons fuel, alcohol fuel, or syngas, or hydrogen, sure the impact in order to decrease the carbon footprint will increase itself. It has to be considered that to consider ammonia as fuel for compression ignition engine without any help for ignition, we need at least the compression ratio higher than 35. So what are the possibilities in order to use ammonia, pure ammonia? As we know, ammonia, it's carbon-free. Its content is relatively not so far from gasoline, so it's good energy density. It has a very high octane number, so it's great because we can use it with high compression ratio without any problem with NOx. But in the other hand, it's clear that its laminar burning velocity, it's at ambient conditions, is very low, and also its flammability limit is very reduced. So certainly we need something to promote or to boost the performance and ensure stability of engine. And as we have seen in the previous study, it's clear that we will have always a strategy that we have to design in order to mitigate NOx and NH3 emission. So briefly, from a review, what we can know, it needs at least between 5–10% in volume of hydrogen to ensure, in fact, combustion stability for many operating conditions, and perhaps 0% when we will use at full load. But there is no real study until now to evaluate the potential of ammonia as function of a lot of operating conditions in low load, medium load, high load, as function also of the engine speed. For the pollutant emissions, it's similar to what we have seen. It's clear that when we have NOx, when we are rich, we have NH3, but also we have hydrogen at the exhaust when we are rich. So, in fact, I only want to summary and to present you some recent highlights about combustion process in single-cylinder engine. For that, in fact, we use current single-cylinder engine. There is no optimization of piston of chamber design, no optimization of ignition device. Most of the case, we want to improve as well as possible the use of pure ammonia in a premixed, it's a fully premixed ammonia air, and we try, if we need, we try to use only the minimum hydrogen content. Sure, we don't work for the moment to the injection technology itself. So first, we use, in fact, a spark ignition engine from Peugeot. So the compression ratio, it's 10.5, no high compression ratio, it's a regular one with a displacement volume of 0.4 liter. The air on ammonia are fully premixed before to fill, in fact, the engine itself. And we analyze pollutant, but I don't want to focus today about pollutant emission. What it is also interesting, as it was a GDI engine, in fact, the piston geometry, it's particular, which induce, in fact, high tumble motion. So if we look at the effect of the engine speed, so this engine speed between low engine speed until 2000 RPM, we want to guarantee stable condition, so it's IMP variation below 5%. And here I put only one example with an occurrence ratio of 0.9. It's similar to or slightly rich. What we can see, it's without, in fact, hydrogen, I cannot ignite at low engine speed. I cannot ignite also low load, and I cannot ignite with natural aspire operating condition. It's difficult really to ignite at low load, but it is possible sometimes to ignite without any content of hydrogen, and as function of the engine speed. We can see also with a high engine speed, I cannot also ignite without hydrogen. This work is done thanks to a project, ARENA, where we are involved with Stellantis or PSA. So, in fact, the conclusion is not so good. We can run with ammonia, but with a very restricted range of conditions. So the idea is to increase the compression ratio. For that, we use a diesel engine design with a spark ignition. So it's no so different engine, 0.4 liter of displacement volume, but the compression ratio can be adaptive from 14 to 17. And, unfortunately, we changed totally the flow fluid, the internal flow fluid, because we have a swirl ratio and no tumble motion. So this is two ideas front of you of what we can see about the motion, spark ignition engine and the spark assisted compression engine. We have no real flow feed in this direction. So first, if I look what's happened when I try to see if I can go until low load, the engine spinning 1000 RPM, here it's the result that we can have with spark ignition engine without ammonia. This is 0.9 occurrence ratio. This is 1.9. You can see that I cannot go very low IMP. If I add 5%, I can reach lower IMP and so on when I want 10%. But with spark assisted compression ignition, we can see that when I increase the compression ratio in 16 or 17, I reach very low IMP. If I do the same thing, but as function of the engine speed, I can do the same, in fact, conclusion. It's clear that I have good improvement of ammonia combustion with the increase of compression ratio, despite of the change of the flow feed. I don't need H2 in this case. I can extend the low load limit until 1.7 bar of IAP, exactly I did with the reformer, and with very low engine speed. So if I look what's happened about the combustion process, what can I see? I can see that in fact the duration of the combustion is smaller with the spark assisted combustion ignition, certainly due to the change in the pressure and temperature inside the combustion chamber. But if I look at the heat release rate, I can see that what's happened is spark assisted compression ignition is really similar to what's happened in spark ignition engine. What I want to say, in fact, it is not usual ISACI combustion mode. We have no combustion in two phases. The first phase is a premixed flame development, and the second one is more like ICCI. It's not the case with ammonia. here, this is the first time that we can see the flame development of ammonia development inside the combustion chamber, internal combustion engine. So I will do again. So it's SACI engine. The spark plug is here, and in fact, we can see that the first flame kernel it's already convected far from the spark plug, and we have a real premix combustion development. So it's a fully premix propagation. Why? In fact, in spark ignition engine, as we know, the laminar flame speed is relatively low. So, in fact, due to the turbulent length scale that we can have in the engine, the ratio turbulent intensity divided by the laminar flame speed will be very high. And so, due to this slow laminar flame speed, in fact, we will have a thickened laminar flame thickness. Sure. So what about the ratio between turbulent integral length scale divided by thickness? In the case of a spark ignition engine, the turbulent integral scale is around 4 millimeters. So in fact, our flames develop in this area for the combustion regime. So it's more like a broken reactive zone on thickness reaction zone. What's happened in a spark-assisted compression ignition engine? Laminar flame speed will increase due to the high temperature. So first, this ratio will decrease. Also, the laminar flame thickness will decrease in comparison to what's happened in a spark ignition engine. So certainly, the turbulent integral length also increase. As I already told you, I have no tumble, only swirl motion. So in fact, I have not small vortices. So it's clear that from spark ignition engine to SACI engine, I will move, in fact, the condition of where we have the development of the flame. So perhaps in the spark-assisted compression ignition mode for ammonia flame, we are again in the flamelet. Here there is some also new result that we have. We record, in fact, OH chemiluminescence and NH chemiluminescence. So NH it's red here and OH it's blue. And what we can see, as we can perhaps more is here, we have more NH at the beginning and always is before, in fact, the apparition of OH. So we have now to try to explain on to see how, in fact, the kinetics modeling can predict this behavior. And why in SACI combustion mode, I have this premixed combustion regime. Sure, certainly because we are in flamelet regime, but we don't know for the moment. Or there is perhaps some other thing, because in fact, in the emission, we have an important quantity of H2. We can see it's between 0.5 until 1% of emission of H2. And this is also predicted when we did kinetics simulation. And if we look at more in detail, what's happened when we have the beginning of ammonia consumption, in fact, we have the beginning of the flame kernel, and just after, we have, in fact, the production of H2. So perhaps, in fact, the presence, due to the NH3 decomposition of H2 inside the combustion chamber, will enhance sufficiently the combustion to reach premix combustion regime. Anyway, what I want to conclude is, in fact, to use ammonia in engine or ammonia only as well as possible is not so easy because it was only a premixture. Now we have to deal with all these possibilities. And what can I say? It's, in fact, we only know that we know nothing for the moment. Thank you so much.
Okay, I'd like to thank all the speakers for the very nice session. And I think the organizers also, Bassam and Gaetan, I think a very, very nice set of speakers you organized. So we're going to go through some of the questions. Some of the questions have been answered live online, but at the same, I think some of them are worthy of repetition and hearing directly from the speakers. I'd like to highlight, we have about 170 people online today, and at least another 40 here, so well over 200 attendees for this session. So it looks like when we take carbon out of the title and out of the picture, more people are interested in combustion. So actually, I wanted to revisit one of the nice questions from Dr. Diores that was presented to Augustin, and Augustin answered this. It was about the LCOE, levelized cost of electricity, when you're using 100% hydrogen going to ammonia. So can you address that one in person, Augustin? I think it was a good question and a good answer.
Yeah, absolutely. It's a really interesting concept, and actually the question is very relevant because that's what the industry wants to know. What is going to be the final levelized cost of electricity when you compare hydrogen with ammonia? And the findings that we have seen so far, all this is just numerical at the moment, is that depends on the situation. So if you're thinking about short distance, short storage, then what will happen is that the cost of ammonia will go up because you will require then the ammonia production facility to then produce the ammonia. And that obviously is going to add to your cap, and that is going to then be finally put into the cost of the electricity. Whereas if you're thinking about a long distance or long distribution storage, then what will happen is that the cost of ammonia will then start becoming more balanced, up to a point that, according to some data, it should be around 6 months, 8 months down the line in terms of time, and around distance around 1,600, 2,000 kilometers. When you get into those thresholds, that's where ammonia starts becoming very interesting, and the levelized cost of electricity goes down. But still, again, all this numerical. One of the things that we're doing in Flex and Confu is one of our partners, KTH, they're evaluating the comparison of having an ammonia and a hydrogen plant next to each other in the Ribatejo plant in Portugal. And the idea is that they can compare the numbers. So far, what we know is that if you want to have the ammonia facility, again, all those caps and OPEX that you will require will then increase the cost, and you need to find a way to then use the ammonia for another purpose, fertilizer, sell it as a chemical or something to then make the costs. But again, this is research that will be published hopefully by the end of the year.
We have a follow-up from Mr. Malik.
Thank you. Thank you, Augustine. I would like to touch on the last point. Just for general information, we as human, when we produce ammonia, our purpose was to fix nitrogen into the plant's soil. Now what we're suggesting is to burn ammonia and send it back to the atmosphere. So, I mean, why not consider a limited burning of ammonia, producing NOx, producing nitric acid, producing fertilizers in a power plant? So a combination of power plant and a nitric acid, ammonium nitrate, or whatever fertilizer, nitrogen fertilizer. Why are we losing the value of ammonia by just burning it? I understand you can, as a energy storage, that's excellent. It has even more value as a nitrogen source in the globe. So it's and you will be part of the ammonia complex and production complex around the world. So why lose the nitrogen that we have fixed from the air? That's a question maybe you can answer.
Yeah, I think that's a fantastic question. And it goes to the depths of why are we doing all this? And a lot of people that actually work in this area, and all my colleagues now that they have presented, will tell you that we usually get that same question in all the fora we present. And it's going like, how much ammonia do we need? Actually, thinking about just the marine industry that is probably moving into the ammonia, we would need 3 times the capacity that we got for ammonia production nowadays. Just for the marine sector, we're just not taking the transport, the aerospace sector. We would need just a super massive scale to then produce that amount of ammonia. And if we're thinking again of producing power, that again just goes to another level. It's just probably 10 times what we require. So the way that we're trying to present it is just, as you were saying, thinking of a new vector that will allow us to then distribute this stranded energy that hydrogen hasn't been able to do. And then not compete, but actually add to then the fertilizer concept, because you can then produce ammonia, deliver it to places where you can use the fertilizer, and depending on the levelized cost of electricity or the cost that you got on the grid, then think, okay, shall I go for a fertilizer or shall I use it as a fuel? And then giving you more flexibility. That's how we're trying to present the concept. But I completely understand, and I completely agree with you, is we're just finding another way to then again distribute this energy, and doing it with nitrogen, hydrogen seems to be feasible. Demonstrable is something that we're going to do probably next few years. Again, things are taking over in Japan, and I think Akihiro can add on that. And also obviously the work that companies like Siemens and some others like Mitsubishi are doing. But that is the question. That is, why are we doing it? And that's what we need to demonstrate as a group working on this subject.
Bassam Ali here. Just want to add that the school of thought about producing fertilizers that says that perhaps we're doing with nitrogen what we did with carbon, is that we're capturing nitrogen from the air and we're putting it in the soil, because once it goes there, it stays in there. While in fact for combustion, it's the other way around. We're taking it from air and returning it back to air. So maybe predicting what's going to happen in 100 years is that we need to think about how much of the nitrogen we're putting as a fertilizer as well. But, and I haven't looked at it closely, but actually there's people who've written about this, is that is now the nitrogen cycle instead of the carbon cycle.
Okay, I would like to ask a question to Jenny. I know on the last slide you showed about this vision for a 100% hydrogen turbine. What scale are you talking about there? Is this the 70 megawatt or several 100 megawatt turbine? What's the objective there?
Yeah, for the last slide I showed, it's just a demonstration facility. So the electrolyzer we have is 150 kilowatts. But the demonstration is more.
Okay. Is it possible maybe come a bit closer to the mic? We're unable to hear you clearly.
Sorry, maybe
It's getting better already.
Yeah, okay. No, this is just a small demonstration plant. So the electrolyzer is 150 kilowatts. But our intention is to illustrate how our power plant.
I don't know if anybody else. Akihiro, can you hear her okay? No, I think there's a problem with the microphone.
Okay. I struggle to find the settings. Sorry for this. Hello, can you hear me now?
It's better.
It's better.
Yes, thank you.
I'm not sure I'm on. Yeah, here we go. Here now it's better. Yeah, I was saying this demonstration we are building is just for to illustrate the principle of a power to X plant. And the electrolyzer is 150 kilowatts, so it's a very small sized. It can't take the total amount of electricity we are producing from our turbines. It's far from that size. But it's more to illustrate and to inspire our customers to realize such plants, but in the real scale.
Okay, thank you very much. We had a question for Akihiro. It was regarding rich combustion. Did you measure the flame speeds? I think it said above 1.2. And were there any challenges with that?
Actually, no. For pure, can you hear me? Actually, no. For pure ammonia flame, our study is the study presented here is based on my paper published in 2015, which is the pure ammonia flame at room temperature condition. Because of the very slow burning velocity, we can't measure the very rich condition or very lean condition. The flame, the shape changes significantly due to the buoyancy effect. However, for ammonia hydrogen mixtures, we measured burning velocity up to equivalence ratio of 1.8, which is was published in the Japanese Combustion Symposium, and we are now preparing for the publication. Is it enough for the answer?
Yeah, thank you very much. Maybe a question to Christine, given that she's looking at ammonia for internal combustion engines. There's a question that can the toxicity of ammonia and the public perception of ammonia as a fuel be a major problem and a barrier to its use?
Sure, it will be. But there's plenty application of internal combustion engine without consider, in fact, personal car, like engine for roads, engine for mining, engine for many things. Engine also for trucks and distribution around the port, engine for marine application. So for the moment, I don't know if they will have an application on the road, but for long trucks, long travel trucks, I think it could be an opportunity. So we have to work still on it, and also about toxicity. It's clear that ammonia is toxic, but we know that there is ammonia everywhere. I think people doesn't know that. We have a lot of cryogenic system for food everywhere. I look on my region, and in fact there is a map where there is everywhere ammonia. I mean ammonia to freeze chicken, ammonia to freeze many things. In fact, we have ammonia distribution everywhere. So perhaps we could.
Okay, thank you, Christine. Can we get the microphone to Thibaut? One of the members, I think it was Professor Okafor from Japan, was asking, or maybe it was somebody else, about the scientific reasoning behind the decrease in NO as you increase proportion of ammonia in the ammonia hydrogen mixture. So it says, what is the reason for decrease in NO by increasing proportion of ammonia in the ammonia hydrogen mixture?
All right, yeah, thank you for the question. So what we understand about the fact that there is so much NO in these ammonia flames, it's because it's formed through fuel NOx pathways, and it's basically very dependent on the OH concentration. So the higher the OH, the higher the NO. And so I guess as you progressively enrich your mixture with hydrogen, you're prone to produce more OH and then prone to produce more NO. I think that's one answer.
And the temperatures the same, flame temperatures? Are you matching these between the different mixtures?
No, we are not looking really at matching temperature. What we are matching is thermal power usually, because this is what makes sense practically. But since most of the NO is not produced through thermal pathways, I guess this is probably not a driving parameter.
Okay, thank you. Mr. Malik?
Sorry, I come from fertilizer industry, so all my questions will be related to nitrogen as a fertilizer. But as you're familiar, probably that ammonia and ammonia salts have very interesting explosive, but also fuel properties. Like ammonium nitrate salts mixture, it's actually a liquid in atmospheric conditions. And it's roughly 4 moles of ammonia versus 1 mole of or 2 moles of ammonium nitrate. Has this been considered as a fuel as well? It's also in the ammonia family and ammonia burning family. I don't know if you can comment on that.
Yes, it has, but not for the applications that we're looking at. And the reason mainly is the health and safety. So it has been used for rockets and high propulsion systems, but not for this particular situation. It's similar to hydrazine, that as well, again, is a compound that is produced from ammonia. You just add the additional, the removal of hydrogen and nitrogen. But it was so nasty that, again, it's just used for auxiliary applications, nothing more. So yes, it has been considered, but again, not for something that has the potential of global deployment.
Thank you.
Thank you. I think that there was a good question by Monsieur Olivier Messager, who was, I believe, back in France now, who used to be here at KAUST. He asked a question about sensor requirements for engines, and I would like to have Christine answer this one live. So the question is, are there any needs for improvements in metrology, either in turbines or vehicles, when dealing with these types of low carbon fuels?
So for vehicles and yes, vehicle application, there is a lot of issue on that because first, for example, usual lambda sensor cannot be used if there is any ammonia slit. So we have to manage, in fact, to control the occurrence ratio with a control unit with another sensor. For the moment, I don't know. There is also, we have also to control the hydrogen emission that we can have in the case of ammonia as fuel. I said that is due to the kinetics, but also we can have also some problem due to, in fact, NH3 can be, we can have some NH3 in some ice, and after we have NH3 after the flame. And due to that, in fact, we decompose NH3 inside the combustion chamber, and we have more H2 at the exhaust. So we have to develop sensor for NH3 and NOx because the quantity of NH3 and NOx is not similar to what you can have with SR. And lambda sensor, an equivalence of lambda sensor, and also H2. And this is not so easy because due to the high level that we can have, in fact, usually we cannot measure everything.
Okay, thank you very much, Christine. A rather technical question from Ping Wang to Augustin about your LES modeling. So he says when he was doing LES modeling, the contribution of subgrid scale combustion in the case of ammonia LES modeling is not as big as LES for methane combustion. So did you have any issue, or did you find any challenge when you use a normal LES grid size when you use for methane for say an ammonia flame?
That's a really interesting question, and I don't have the answer. For that one, we've been collaborating the part on the numerical analysis with Tokyo Gas. So I can definitely give you that and send you those details as we are now collaborating. But I'll get back to you, definitely. I got your details, and yes, it will be a pleasure to give you those values.
Very good. Did anybody here doing the LES? I know Professor Hong's team is doing DNS. I'm not sure if they're yet at the LES for ammonia. I don't see Francisco. Paco's not around. Okay. So even our CFD expert in-house is not here to answer this. But good question. And again, you have the contact information for all our speakers on the website. Feel free to reach out to them. Are there any questions from the room? Yes, Christian. Can we, Bassam, can you pass the...
Hi, Professor Agustin. This is Christian from KAUST. I'm really curious about the APU you are running there. So have you been able to run in pure ammonia or ammonia hydrogen blends with the actual combustor of the APU, or are you using another combustor, external combustor? Can you expand a little?
Yeah, absolutely. So we're going to be running with a new combustor. And the way that we're doing it is a manufacturing in 3D printing. We have done the assessments we're using CFD. And the main reason is that the systems that we got is an APU with a combustor probably of 35-40 centimeters length. When we did initial calculations using CFD, the length and the system itself weren't good enough. The residence time wasn't enough to then give us the combustion that we were after. So that's the reason, because we thought, okay, the best way then is to then reconfigure the system and then using it for that purpose. So the way that we're going now is we had an annular combustor, we're then changing it to a CAN type combustor, and this fits into the research that we're doing for Siemens as well, for the SGT 400 unit. So yeah, that's the way that we're doing it. And hopefully, the plan is that in 6 months, 7 months from now, we'll have it running. And again, for students like yourself, if you're studying, if you're an academic, the same thing, this will be open for you to then come and then have a look.
Thank you.
Hello, this is Diana from KAUST. I have a question for Jamie. You showed some results about the stability of the hydrogen combustion and compared to the natural gas combustion. And you showed that basically it was as stable or even more stable with the hydrogen. Did you do similar tests with ammonia yet? And do you expect to have problem of stability with ammonia? I'm talking about dynamic stability, thermoacoustic instabilities.
Thank you, Diane, for the question. The test I showed was running on a full-scale gas turbine, an SGT-600, and we measured the dynamics in the annular combustor, and we measure in 3 different bands, so frequency bands. So it was kind of simplified global phenomena that we saw there, and that it stabilized. And we think this is this axial flame movement that is prevented. But for sure, there are also other thermoacoustic phenomena. In an annular, you could have tangential modes kicking off. But for this frame, it's not so likely because the combustor is film cooled and that kind of acts as a damper. So this would be more maybe concern for the SGT-800, where we have a completely sealed combustor. We have not come close yet to feed ammonia into a real gas turbine full scale. We are still on the laboratory and atmospheric testing. And this is partly linked to EHS, handling ammonia in the test beds in such large amounts. But also not as much push from our customers as we have on hydrogen. On hydrogen, we have both existing customers asking if we can do upgrades, and we have new customers wanting to have a future-ready, hydrogen-proved design. So it's a very different request. But I would like to study ammonia, and since ammonia is another low-grade fuel, we do think it could be a challenge with thermoacoustics, definitely. We will call you then.
Thank you.
Okay, I'd like to thank all of our speakers today. I'm going to give 30 seconds closing comments to our speakers, our panelists. Let's start with Augustin. Any closing comments?
Yeah, I think that the interesting thing about using ammonia is that it opens the possibilities of doing research, especially in combustion and energy science. And it's just exciting, it's fascinating, and we're just finding out that there are many things that we didn't know about it. So if you're interested in it, it would be great that you get in contact with any of us. And obviously working through KAUST is always a fascinating experience to do so. So yeah, keep doing it, it's lovely, and that I can conclude.
Jenny?
Yeah, thank you very much for inviting me here, and a lot of interesting talks, and I encourage all of this research to continue, and we need to speed up. We need to also do demonstration on the full engine level, so we need to figure out how to get there faster, I think. So thanks again.
Thank you, Jenny. And Akihiro, Japan's leading the way in ammonia. Tell us some closing comments, what you're noticing there.
Thank you very much for the invitation for this interesting workshop. So actually the many ammonia study is performed in many countries and university and industries. So the communication and the discussion is going to be important. So we shouldn't focus on our own studies, and we should discuss each other about the ammonia combustion to enhance the utilization in the industry. Thank you very much.
Thank you, Akihiro-san. Christine?
Thank you so much to invite me also. I think to study ammonia combustion, it's a very exciting thing because, as you know, it's toxic. We cannot burn it very easily, but in fact, it burns. So it's something like incredible, and we don't know for the moment why. So we have many things to do, so it's great. Thank you.
Thank you very much. And Thibault?
Well, also thank you for the opportunity. So I don't have much to add, but so I'm glad that now we finally found an opportunity with Cardiff to start collaborating in the lab. We are starting also to talk with Christine about converging interest into flame chemiluminescence. And so I'm really hoping that we can also do something similar with the Tohoku team and NTNU in Sweden. So we need to start talking more.
Okay, thank you very much, everybody. And in the spirit of sharing of information, collaboration, I think I'd mentioned KAUST, Tohoku, Cardiff. They have a young researcher consortium, so to speak, around ammonia. And also later this year, the ICFD conference hosted by Institute of Fluid Science in Tohoku will have special ammonia hydrogen session. And in addition, ASPAC, which is the Asia Pacific Combustion Conference in December in Abu Dhabi, which is jointly hosted between KAUST and Khalifa University and chaired by Professor Hong Him and I think it's Dimitris Karitsis. They'll have a special session, special workshop on ammonia and ammonia hydrogen combustion. So again, a lot to come, and hope to see you all in Vancouver at the symposium. I'm also talking about ammonia there. Okay, have a good day, and we'll be back in 20 minutes after a short break.
Would do. Yeah, hybrid mode. This is the first time I've done this. Can you tell? Yes. If you'd like to present, yes, please. You have missed your introduction.
Well,
Sorry about
I'm
that.
sure you said wonderful things about me. Thank you so much for
Well,
those kind words. I'm very glad to be able to hear you now.
Yeah, okay. Catch it on the recording then.
Beautiful, beautiful. Let me share some slides. And I'm going to talk about the role of ammonia in decarbonization. And I'm not going to be very technical. So I think we've got a lot of wonderfully technical presentations today. I'm not going to do that. I'm going to talk about the bigger picture, where the context for combustion technologies fits in, and where the role for ammonia fits in a sustainable energy economy. So my name is Trevor Brown. I'm the Executive Director of the Ammonia Energy Association. And just a couple words of background. The Ammonia Energy Association, we were established in 2004. This year will be our 18th annual conference on the topic of ammonia, combustion, fuel cells, consumption in energy applications, and of course the decarbonization of ammonia production. So low carbon and carbon-free synthesis technologies is the topics that we've been driving forwards for 18 years now. You may imagine 18 years ago, this was not a commercial area. We are just beginning to see a tremendous amount of interest in ammonia as a very nearly commercial opportunity for industry. But we're still at that tipping point where there's just a tremendous amount of knowledge that people haven't yet ordered and understood and put into place. There's not a tremendous amount of question marks on the bigger picture, but there's a lot of knowledge gaps between different sectors. And so that's one of the roles that we try to really address, specifically since we relaunched as a trade association in 2018. We're trying to build bridges between different regions, different countries and regions and continents, and also between different sectors, so that the hydrogen sector is talking to the maritime sector, is talking to the fertilizer sector, is talking to the utilities. So lots of different groups. We've got now 111 corporate members in our association from around the world, really representing just a tremendous diversity of different applications, different production pathways, green, blue, turquoise. I'm not a big fan of the color coding, but let's rephrase and call it carbon-free production technologies and low-carbon production technologies, as well as a whole range of different industries like maritime and the hydrogen sector. So I'm going to briefly do some introductions of various sectors where ammonia has a really pivotal role. In some of these sectors, that role is very well understood. Fertilizer, we really don't need to spend much time talking about how we need ammonia in the fertilizer sector. We've had 100 years to develop that business case. We've had 150 years to develop the business case for ammonia as a refrigerant. But that's in terms of volumes, that's a fairly small market. In terms of handling and operations and safety know-how, that is a tremendously important market for us to be understanding and making sure that knowledge sharing is transferable between different sectors. But I'm just going to give a broad overview of why we're having this conversation. And the first is with fertilizers, and this is the existing market. So say we never did anything new with ammonia, we just carried on business as usual. We would still need to decarbonize roughly 180 million tons per year of ammonia capacity. That's somewhere close to 1,000 ammonia plants around the world. that's quite a big lift. There's a lot of work to do, and if we're planning to do it by 2050, we have a very few number of investment cycles to achieve that. And so what's useful to think about is the role of the revamp versus the greenfield build. And the slide that I've put up here is referring to the Yara plant in Western Australia in the Pilbara, where they're just moving forward now with their installation of the PV system and the electrolyzers to add on 3% of their hydrogen coming from renewables in a world scale 850,000 ton per year plant. That is phase 0, where we're just dipping our toe in the water and seeing how electrolyzers work. The next step is, of course, expanding that to a larger percentage. Phase 1 is at 20% of electrolytic hydrogen as a feedstock. Phase 2 involves building a whole new ammonia plant and running 2 ammonia plants side by side, increasing the green ammonia production to over 500,000 tons per year by 2030. Phase 3 is ramping that up further and expanding the renewables inputs and similarly reducing the fossil inputs as well. So this is 1% of global greenhouse gases that we're trying to mitigate, and it's a really important project. And the relationship between decarbonizing fertilizers and the use of ammonia in energy applications is very intricate and exciting, because for an ammonia producer, what we're looking at here is a massive expansion of market volume. Let's talk about that. So the next illustration of a business model for ammonia in energy systems would be looking at the very simple argument of ammonia having more hydrogen than hydrogen and more easy to store than hydrogen, and the fact that after you've made, if you're making ammonia, the cost of making hydrogen is about 90% of that. So if you are a hydrogen maker and you want to add on a 10% final step to bring yourself a product that is easier to transport and store, the incremental investment required is in fact quite small relative to getting hydrogen in the first place. Once you've got that hydrogen into ammonia, it's easier to move and it's easier to store. And that allows you to reach new markets with it that you wouldn't be able to reach with hydrogen alone. The slide here, I'm sure everybody is familiar with. This is the Saudi Arabian NEOM project. That the slide is from the Airgas presentation, where they're talking about their business model of ammonia for global distribution and then cracking at the hydrogen refueling station. We're talking about heavy duty trucks and buses here. And so ammonia as a renewable energy commodity, or a low carbon energy commodity that can be traded, transported and distributed around the world to support a resilient supply chain for large scale adoption of hydrogen. This is not ammonia in competition with hydrogen. This is ammonia enabling the hydrogen economy and lowering the costs of it. If we look at the maritime sector, well, this is a very interesting business case, because outside of the Ammonia Energy Association, there was nobody in the maritime sector talking about this in March 2018. In April 2018, the International Maritime Organization published its initial greenhouse gas strategy, which set many different targets. One of them was an absolute 50% reduction of carbon, of GHG emissions by 2050 versus a 2008 baseline. Now, what this gives you is a very clear business case for a carbon-free molecule. And that business case hadn't really existed before the International Maritime Organization made that target. And so the importance of that, I really cannot understate, because understanding how to convert a technology portfolio into a business case is absolutely critical for any of these combustion technologies to actually be adopted in the marketplace. We need to have, you know, in Business School 101, we talk about what problem does your product solve? And if climate change isn't economically a problem, if we're not developing a carbon tax or requiring certain amounts of products to have a zero carbon footprint, if we don't have those regulatory drivers, then there's no problem to solve. There's no underlying business for something that is inherently more difficult to do than digging up fossil fuels and burning them for essentially free. So with this IMO initial GHG strategy, we suddenly have a 30-year runway for ammonia combustion technologies in a global sector. And it's a very manageable transition because the number of assets is relatively small. We're talking about ships that you can count. You could actually make a list of them and say, these are the ships we need to revamp. These are the ships that we need to convert to carbon-free fuels. And you can make a list of the ports where you need infrastructure terminals and bunkering to be available. And of course, you can start by using vessels that already handle and carry ammonia and go from one ammonia terminaling port to another ammonia terminaling port. If you count those vessels up, the ammonia carriers and the LPG carriers, you come to roughly 2% of the fuel use of the global maritime fleet. And so if you look at this slide that I'm illustrating my talk with here, this is from the COP26 Climate Champions Getting to Zero Coalition, looking at the S-curve of adoption of zero carbon fuels. The numbers that they have are specifically relating to ammonia in the fuel mix. And that 5% by 2030 refers to the 5% of the global maritime fuel mix. So market share for ammonia in the fuel mix. Translates to roughly 60 gigawatt of electrolyzers producing 30 million tons of ammonia per year. That displaces about 16 million tons of heavy fuel oil. If we're going to hit the targets up to 2050, we're talking about a terawatt of electrolyzers. And the sooner we start talking about producing low carbon molecules in terawatt scale, the better, because this is what's required if what we're doing is decarbonization. So the maritime fuel case is a relatively well understood one, but I just do want to stress the point that 3 years ago, nobody was talking about it. 3 years ago, if you look back at the headlines, you had all of the CEOs of various maritime companies saying, "Oh, we need to go and invent a new fuel." And a number of the people in this room would have put their hands up and said, "Well, I know some options you could use," because of course we'd been working on ammonia for much longer than that. But the speed at which this industry has come to recognize the role for ammonia, and I'm not suggesting ammonia is the only option. Of course, we're going to have hydrogen vessels, we're going to have electric vessels, we're going to be using wind propulsion and energy efficient design to the maximum, because ammonia as a fuel is going to be inherently quite expensive. And the value of energy efficiency and direct electrification. So for example, cold ironing. There's no point running an engine, burning an electrofuel, if you could just plug in at the port. So when a ship is at port, it is going to be very expensive choice to run your engines, and a much better choice to be plugging in. The phrase for that is cold ironing. But the speed at which the industry is educating itself about its options and demonstrating and doing the work to develop the hazards and the regulatory pathway for all of these things to be safe and responsible is fantastic. And the reason I'm making such a point about the speed and the moment that the maritime industry sort of grasped this challenge is that I believe that the electric power industry is about 6 months away from a moment like this, where it recognizes that ammonia as part of the future technology portfolio provides opportunities for an electricity system, for an energy system, not just the grid, because we're going to have to get much bigger than the grid. If we look at these numbers, we've got a terawatt of electrolyzers running by 2046, and that's going to be, you know, grid and that much again. So the question is, where is the electricity sector, if there is such a thing? I'm sure there's dozens of different electricity sectors with different drivers in different markets and regions. But when will ammonia as part of that option set become properly recognized and properly modeled in energy system analysis? Here's an example. So this is published by NREL last week. And this is one of the first really good graphic illustrations I've seen of the difference between an incremental investment in decarbonizing the grid versus a systemic investment in decarbonizing the grid. So if you look at this little square chart on the right here, where you've got levelized carbon dioxide abatement cost, dollars per ton, which starts at zero. The paper here is discussing the US electric grid, and it's saying with the existing policies we have and the existing economics of the different option set, we can reach a 57% penetration of renewable energy at zero cost of carbon abatement, because wind and solar is just very cheap. But driving it further than that, trying to reach 100% becomes very expensive. Not, however, if what you're looking at is the levelized cost of energy. So if you're looking at the levelized cost, the increase is not terribly big, because these final percentages, while very expensive, are relatively small. They're only 1%, 2%, 3% of your total energy mix. And so this is a really interesting illustration of the role of synthetic fuel combustion in a decarbonized grid, where you are opting to deploy very expensive power generation in order to achieve zero emissions. One of the interesting pieces of detail here, if you look at the color bars on the left-hand side, is the impact of capital on this. You've got a steep increase in this blue section that represents the capital component of your system cost, where because you're building combustion turbines that you're going to use very infrequently, only when there is significantly not enough wind and not enough solar in your highly renewable system. You're needing to provide things like seasonal energy storage and multi-day storage. That's when you have a very significant capital cost of your system, because you're using things with a very low capacity factor. You also have an increased fuel cost between 95% carbon-free and 100% carbon-free, because you're paying more for a fuel that you've already synthesized from electricity. That value-added product is always going to be more expensive than your average electricity generating option. And so when you look at this, remember, this is not an argument against using ammonia as a fuel. This is understanding why an expensive option like ammonia is completely worth it and valuable, and understanding that while it may be incrementally expensive, it provides the option set that underpins a carbon-free grid. And without it, and this analysis is in fact also in the NREL paper, I recommend it to all of you. In fact, the whole bunch of energy analysis that's come out of that team is really wonderful. But they ran a scenario in which there were no ammonia combustion turbines. Well, they didn't go as far as ammonia. There were no renewable energy fuels combustion turbines. They were broadening it to whether it's hydrogen fuel or ammonia fuel or other synthetic electrofuels. If you take that option set out and say we don't have a renewable fuel combustion turbine in our future electricity grid generating portfolio, the cost, the system cost, these charts on the colorful bars on the left get 20% bigger. So while this is an expensive incremental technology to add, it has a significant lowering of the system cost if what you're trying to do is achieve a zero carbon grid. So this is tremendously important work that begins to support the demonstration of an actual market value for something like ammonia as a fuel in a power system. We don't really have a very good way of valuing long-term energy storage, long duration energy storage, or the ability to use otherwise curtailed energy or overbuild renewable systems to be producing fuel. We don't have a great economic toolkit for modeling this, for modeling what that product is worth. And so this is very interesting. But the context of this kind of analysis is from a perspective that I begin with, which is always, if we're trying to decarbonize, what we need to do is essentially electrify everything, because direct use of electricity is going to be the most efficient use of energy. And only when you cannot directly electrify are you going to turn electrons into molecules. And you're going to then, the first molecule you're going to use is going to be hydrogen. If you're not using that hydrogen locally, and if you're not using it pretty quickly, if you have to store it or transport it, you're probably going to end up converting it into a more complex molecule, whether it's methanol or ammonia or LNG. We've got lots of options. But that logic only stands if you have renewable resources. So if you happen to be a country like Japan or South Korea, where you use a lot of energy in your economy, but you don't have a lot of low carbon resources, and you're importing energy, it's very difficult to import electricity. You're probably importing molecules in the first place. And if you're importing molecules in the first place, you're probably not going to turn them into electricity in order to fire up an electricity first energy system. You're probably going to use a molecule first energy system. And so that's why we have projects like the one in Japan, where what we're looking at is a really aggressive deployment of ammonia as a fuel in the power system. This would make almost no sense in the United States, but it makes absolutely sense in Japan. And here we have, I'm sure that that somebody else has already shared these slides during this conference. Japan's roadmap for fuel ammonia, looking at ammonia coal co-firing, and then moving to the ammonia gas turbine to be providing 100% carbon-free electricity in the 2050 timeframe. So these are the different sorts of applications that we have with ammonia, the different kinds of contexts where ammonia has a terrifically important role in decarbonizing energy systems. And I really wanted to illustrate for you the role that those combustion technologies are going to play in both that energy, renewables rich kind of jurisdiction or region like the United States, where you're going to be working on an electrification first principle, versus the energy importer, where you're probably working on a molecule first principle, and the profound difference that makes to the technology set and the incremental investment decisions that we need to be making. And that is the last point that I wanted to make. I guess the final thing I would say before I close out for any comments or questions, and then looking forward to the panel discussion very much, is our annual conference will be going ahead in person in Boston in November. If any of you wish to join us, you would be most welcome. Thank you very much.
Thank you very much, Trevor. We're going to save, in looking at the time, we'll save questions till the panel discussion, if that's okay. And so with that, I'll move on to the first of the invited speakers. The next speaker is Andrea Gruber, who holds a doctoral degree in mechanical engineering from NTNU and is a senior research scientist at Syntef Energy Research and an adjunct professor at NTNU. He's spent nearly 2 decades in close and fruitful collaboration with combustion researchers at Sandia Lab and has initiated the deployment of direct numerical simulation on some of the research challenges related to combustion of highly reactive and non-standard fuels in gas turbines, with hydrogen in particular. And he's going to talk to us about fundamental characteristics of turbulence chemistry interaction in pre-mixed ammonia, hydrogen, nitrogen air flames. So thank you. If you'd like to start your presentation, Dr. Gruber.
Thank you, Mr. Chairman. I'll try to share my screen first. Is my screen visible now?
Yes.
Thank you. So, thank you for your kind introduction. I will go now to a nitty-gritty details level compared to the previous speaker. And actually, the previous speaker provided an optimal introduction to my first slides. What you see here is a flame going through the color spectrum from hydrogen, the invisible flame at the beginning, then to methane, then ammonia, then hydrogen ammonia, the white color flame at the end. This is a bit a metaphor for what I'm going to present today. So first of all, some acknowledgement about my co-authors directly involved in the results that I will present. I will not cite them all by name, but you see that they are mostly my colleagues here from Trondheim, Syntef and NTNU. And Jenny from Siemens that spoke earlier today. And also my collaborators in the US, Professor Foreman Williams at UCSD and Jackie Chan at Sandia. So I would like also to thank our sponsors, the CLIMIT program of the Research Council of Norway, Gassnova, Siemens and Equinor that have funded this work. So a quick outline. First background slides, then I will quickly explain the methodology for those that are not very familiar with it. Then I will present the main results regarding turbulent chemistry interaction and provide a quick comment on the implications that this has, and summarize and conclude. So very quickly, these slides, we have seen them earlier today. In brief, especially for stranded resources, ammonia is clearly a competitive energy carrier. I usually like to use this diagram, which shows on the axis the distance that the energy carrier has to travel between production and usage, or the time period for storage. And you see that you go, as the previous speaker said, if you make hydrogen and you can use it after a short time and don't move it very far, then you probably just keep it as hydrogen. But if you are going far or have to store for a long time, then ammonia begins to make sense. I was inspired in starting this work really from my relationship with Japan, where I spent my postdoc years at Sansoken, so the ICE Institute, and of course the work at Tohoku University. In the end, I think that the choice of ammonia versus hydrogen is a matter of a case-by-case basis, in summary. So also another important point is that, and that probably was not emphasized enough today, we are using thermal power cycles today to burn fossil fuels, but these cycles do not necessarily need to be dirty, right? In fact, they have a huge advantage for higher power rates because they use a very small amount of fuel to leverage on a huge quantity of air as working fluid. This is a significant advantage against electrical or electrochemical conversion systems. So the main takeaway is that these machines are not intrinsically dirty, but as clean as their combustion technology and the fuel they utilize. So a simpler chemically simpler fuel can result, in fact, in a very clean exhaust. So what are the challenges here? Well, the key factors in the design of a combustion system include the combustion velocity, the fuel reactivity and flammability, and the flame temperature. There are others, but these are three main ones. And as you see, for methane as a reference fuel, hydrogen and ammonia, we have a very wide variation, with hydrogen being too reactive and ammonia being too little reactive. So the proposed concept that I proposed to Siemens and Equinor in 2016 is, can we use hydrogen ammonia blends as carbon-free step-in fuels for natural gas? There are important differences between these three fuels, but perhaps this difference can be reduced by mixing them optimally. So, and here, in places where waste heat from the thermal machine is available, this gives the possibility of actually using this heat, recycling it to crack the ammonia and then intrinsically increase its low heating value, and achieve also a mixture that is whose nominal combustion properties are similar to those of methane. I was inspired in this thought by the seminal paper by Verkamp on the Combustion Symposium 1966, and of course by later works. But I think that this was one of the first ones that proposed this, from Allison Research Center in the US. So as you see, you can make a mixture that replicates very closely the combustion properties of natural gas, of methane, as representative of natural gas. Regarding the methodology that we use, it's direct numerical simulation, and this, turbulent combustion is there is a tyranny of scales. We go from the scale of the combustors to the scale of the molecular interactions, really. Of course, with DNS, we do not resolve the discrete, but we stop at the continuum range, so in the range of microns. And the chemical reaction is rate controlled by the small scales of motion in all turbulent flames. And this means that RANS and LES-based model, which make assumptions at these scales, cannot provide physical insight. Experiments on their side have progressed hugely, limited, but they are limited by the spatially and temporally resolution that they can achieve, and also by the data completeness. By that I mean the possibility of measuring simultaneously multiple quantities. This is very limited. So ultimately, industrial application will need experiments, but we have to look elsewhere to gain detailed physical insight. And I will come back to this with the main results section. So what is DNS? DNS, according to the definition provided by Coleman and Sandberg here, is a numerical experiment producing a series of non-empirical solutions from first principle for a virtual turbulent flow. It provides complete knowledge unaffected by approximation, and there is a start there, at all points within the flow, at all times within the simulation period. The star is because chemical kinetics and radiation and soot and multiphase, of course, complicate matters. But for homogeneous reactions in gas phase, I think that this, and for fuels that are relatively simple, like hydrogen ammonia, I think we can say that this is true. So the computational domain size must include the largest scales and the smallest one of the flow. And this creates a very strict requirement on the amount of flops or floating point operations that are required. And this represents the limit then, as you may understand. And we are presently limited to Reynolds numbers about 10 to the 4th today. In other words, DNS can provide unprecedented insight into key rate control in physical processes, but it cannot be a brute force solution to engineering problems. So what did we do? We started by developing, in collaboration with Forman Williams, this short chemical kinetic scheme that is usable in LES and DNS, but still accurate. And at the same time, we also started looking at this, at the difference between flames that are nominally identical, but exhibit very different behavior. Under strain, for example, the ammonia, hydrogen, nitrogen flame, which has nominal properties identical to the methane flame, or very similar to the methane flame, has a resilience to strain that is 5 times larger. So this finding led us to the next experiments in which we actually, this is an experiment, it's not a DNS calculation, but in which we measure blowout in turbulent flames. And this was very surprising. The blowout limits of these premixed turbulent flames of ammonia versus methane showed us a tenfold increase in the blowout limit. So the blowout velocity was 120 meters per second for the ammonia hydrogen flame and 12 for the methane flame at the same nominal conditions, right? So the only difference here is caused by the presence of hydrogen, we will see. In connection with that study, we performed a DNS of a turbulent flame comparing the ammonia blend with methane, again, with identical laminar flame properties. And we observed a very different behavior with a strong acceleration of the flame. You see the I naught factor here that normalized the fuel consumption by the, by the flame surface. And it showed very clearly that this hydrogen ammonia flame is accelerating enormously compared to the methane flame. And this was the first observation that we did about this, and we ascribed this to the role of diffusion at the leading points of the flame, as I show here with increased red color in the OH mass fraction, where at the same point where the elemental mixture fraction shows an increase in the hydrogen content. This led us to other studies where we looked at the role of curvature in NOx formation and NO2 formation. And this is just published in Combustion and Flame. I will not dwell very much on this study because I think the next slides are the most interesting. However, I just want to indicate the fact that this study that span a lot of different equivalence ratios also show that the diffusive effects are important even for pollutant formations. So our ongoing work is really on comparison of ammonia hydrogen flame at 1 versus 10 atmospheres. And here we designed a case to place 2 flames at 1 and 10 atmospheres on the same place in the regime diagram. So this is the regime diagram as I show here. And these flames, when the regime diagram is built with nominal properties, are in the same place. However, they look very different. And this, I want to focus on this slide and the next, because it's a very interesting finding in my view. While the flame on the left at 1 atmosphere shows a very clear sign of being in the distributed reaction regime with a lot of thickened preheat layer, and basically the flame is shred apart by the strong turbulence. On the right-hand side, at 10 bar, we see that this flame is very strong. It's burning very strong in a sort of flamelet regime with a strong superadiabaticity at the leading points. This is, we believe, a new finding because even though the leading points hypothesis was earlier formulated by the Russian school, so by Zeldovich and co-authors, the pressure scaling of this magnitude is a new finding, and can explain actually why a lot of gas turbine manufacturers are having problem in going to high hydrogen content flames at higher pressures, right, for increasing pressure. So you see here the heat release rate at 1 and 10 atmosphere. There is a clear, strong enhanced burning rate that is normalized versus the laminar value. So this is really, it's a pressure effect, really. And this has implication on widely used correlations that are used in engineering and also on turbulent combustion modeling. It means that turbulent combustion model that want to represent this correctly, they have to take into account diffusion, even in strongly in high turbulent flame. This quantifies a bit more what I have shown before, showing the red and blue curves show the heat release rate and the consumption of the fuel as a function of curvature. So the red lines are positively curved, so the convex toward the reactants, and the blue curves shows the trailing edges of the flame, so the convex toward the product side. This is a very significant and uncontroversial evidence of curvature-dependent diffusion reaction process and the strong acceleration of the flame front. The bottom line is that there is a significant role of molecular diffusion, even in high turbulence, so at Karlovitz number 600, as we have here. My last slide, this is actually has been observed before experimentally, this very extreme role of preferential diffusion in turbulent flame by the paper by the Princeton group here, but it was never, no pressure scaling was ever attempted at that time. So this is a to-do on the to-do list, I would say. To summarize, yeah, basically we have observed a strong role of diffusion in these flames, which affects their behavior and has to take into account in the design of combustion equipment at large, I would say, from gas turbines to internal combustion engines. And there is a hint to the audience. It would be really nice to have an experimental study about the pressure scaling effect of this, because I think that's the key to hydrogen enriched combustion at high pressure in gas turbines. That is it. And I guess I'll take questions later.
Thank you very much. Yes, we're going to wait till the question and answer session at 5:30. So with that, I'd like to introduce the third speaker for the afternoon, Professor Gaetano Magnotti. He's one of my colleagues in the Clean Combustion Research Center here in KAUST. He holds a PhD from George Washington University and was a postdoctoral fellow at Sandia National Laboratories before joining us here in 2016. His main research interests are the development of the application of laser diagnostics to study turbulent combustion and enable novel combustion strategies. And his research activities include turbulent oxy-fuel and ammonia flames, supersonic combustion, and high-efficiency internal combustion engines.
Well, thank you, Jamie, for the introduction. And first of all, I want to thank you, all the attendees and the speakers of this conference. I'm one of the co-organizers, and I want to remind one of the objectives for us to do this conference is actually to invite you to collaborate with us. This is one of our main objectives with this conference, and I hope that with this presentation, I can stimulate that collaboration even more. So the title is Advanced Laser Diagnostics for Ammonia Flames. This is the work of mostly one of my PhD students, Ao Tang, and postdoc Chabo Yang. And there's again, Thibaut helped us quite a bit with this project, and Koxing has helped with the NOLIF. That's actually mostly his work. Of course, I thank KAUST for funding this project. So Andrea actually gave me the perfect introduction for this talk, because he highlighted the need for more experimental measurements, in particular for quantitative measurements. We have seen during this day a variety of flames, going from actual gas turbine to some technical combustors and simpler flames, but the amount of quantitative data is very limited. And this is a research direction, because we are pursuing here at KAUST. In particular, there's a need to advance diagnostics for 1D Raman scattering, so we can get measure species and temperature. Andrea just mentioned, normally in these ammonia hydrogen flames, we have seen some picture qualitative of 1 or 2 species, maybe simultaneously. With the 1D Raman, although it's 1D, just 1D measure for now, we can look at all major species at once, we can get the temperature, and we can couple to quantitative plate measurements, such as NO, NH, and other quantities, for example, NH2. I'll talk briefly about that. What can we do with this? We can, of course, study some of this more technical configuration, but we can also do something analogous to the DNS simulation, trying to answer fundamental questions of combustion physics. For example, turbulence-chemistry interaction. This is, of course, very important, especially if we're burning pure ammonia. Preferential diffusion has already been shown in the previous presentation to the DNS. And yes, we're looking into that. We want to look at the role of preferential diffusion in and the effect of pressure, and we're developing the tools to do that, as well as ammonia cracking in situ, especially if we're looking for configuration going toward the mild combustion or jet knock-off flow kind of arrangement. So why 1D Raman scattering? It provides temporary spatial resolved measurement, all the major species we get at once. We can get temperatures also in enclosed combustors, just applying ideal gas law, as I'll show later in this presentation. And we can get a lot of very important derived quantities, such as mixture fraction, atom ratios, scalar dissipation, so they can help the CFD modeling community to improve their models and get then finally enable ammonia combustion even in industrial scale. Also, the knowledge of the composition can allow us to do quantitative plate measurements, so no longer only qualitative pictures, but also real data. And hopefully we can achieve that with high precision. So what I'm going to present today is results that we obtained with this setup I'm showing in this picture here. You can see, you can recognize on the right, this is the pointer, yes. So this is the high pressure combustion duct. You have a KAUST. Thibaut early on today showed many of the results obtained in this combustor. And this is our system for the 1D Raman scattering combined with the NOR-LIF. That's on the other side of the room. We have the laser for LIF. This is in a sense a fairly standard, although there are now very few Raman systems available worldwide, but it's a combination of multiple lasers, low noise CCD camera, and the key is really having a very short exposure time, because as we've seen many times during the day, the ammonia flames are luminous in a very different way than the methane flame we're used to. They look around orange red, even if they're not soothing, of course, but their color is interfering with the Raman measurements, they are in the visible range. And again, I iterate this point that we want to obtain quantitative LIF measurement. This is a more schematic of the setup. So I'll start first with showing some of our laminar flame results. We developed a counterflow burner that can fit in the high pressure combustion duct. The idea, we operated up to 5 bar. The main idea is to have a platform to develop diagnostic, calibrated, and characterized. So that when we can provide the data in turbulent flame, we can give you also the accuracy, the precision, so you can use that in the modeling with confidence. We tested several counterflow flames. We have a library now of 12 flames, I think, we have analyzed with varying composition and strain rate. The unique feature of this counterflow burner is that optically accessible along the axis. So with every single shot of this that we obtain from this flame, from both the LIF and the Raman measurement, can be compared to 1D simulation obtained with Chemkin. And the counterflow flame is really designed to as the ideal 1D burner, 1D flame. And I show that the results actually fit very well with the simulation for a variety of conditions that we tested. Let me start with the NOLIF. Of course, this is a technique that has been applied extensively. For those in the community that are interested in applying when you have ammonia flames, very early on we found out that the usual excitation, Q26, is not ideal. We need to excite at Q36, otherwise we run into issue of photofermentation, absorption from ammonia, and interference from LIF or other species. So the Q36 excitation is much more beneficial, reduce this interference. We run a kind of a standard calibration process, first in hydrogen air flames, see that we know an amount of NO, and then a standard validation in counterflow flames. And you can see here a very, I would say, almost excellent match with the 1D simulation. Now, I want to point out another aspect. In this calculation, you need to know the knowledge of the species. This is we are close to the linear regime, so we cannot do too many approximations to obtain quantitative NO. We need the knowledge of the species. That's this xk in this formula here. How we get the species? We can obtain from Raman scattering. I'm not going to go into all the details, but what I want to underline is that the formula here for LIF looks very complicated. For Raman, we have a very simple relation, linear relation, between the signal we collect, this S here, and the number density of the species. All we need is a linear matrix with terms, then indicating with C here, their function of temperature and, well, the spatial location. This is a detail. A major issue going from the methane air flames that we've been studying for decades to ammonia, or in general to any new fuel, is that the spectra of ammonia, what I'm showing here, are not available. This is was a surprising result for me at the beginning, since it's a relatively simple molecule. But even for simple molecules here, we get tens of thousands of transitions, and creating a numerical model for ammonia is not an easy task. With such a simple approach, we don't need that numerical model. All we need is what we call a response curve that tells us the integral of the Raman signal within this range of wavelength, how it evolves with the temperature. We can use our counterflow flame to calibrate this response curve. And we tested this approach first with hydrogen that's of known quantity. I'm pointing this out because this is a new approach that we're developing, and this can be useful for many other fuels other than ammonia. This was a major limitation in extending Raman to different species. The approach works well. We can reproduce the response curve of hydrogen that was known, and we can then extend the approach to ammonia. Unfortunately, we ran into a major issue. We originally thought that ammonia, hydrogen-nitrogen air flames were Raman friendly, meaning there was no source of interference that would overlap with the Raman signal. But what we see here is we are near the flame front. There's a broadband contribution that's comparable in intensity to the Raman signal. Now, this turned out to be actually an opportunity because running thanks to a series of flames that we collected, over 12 flames, comparing it to numerical simulation, we found that this interference is not as in a hydrocarbon flame related to multiple species and in a sense of almost no diagnostic value, but follows very closely the NH2 profile. And this is without any correction. So there's a great potential here for direct diagnostics of NH2 in addition to the Raman species. And going back to the previous talk, so we're now measuring all the major species, temperature, NO, and potentially, this has to be validated, also NH2. This is more details on the treatment of this interference. We have developed strategy in the past, say, 20 years to deal with interference from methane flames. We can transfer it to ammonia flame. Simply a third order polynomial as functional temperature will do the job. Let's see what the results. Well, then, sorry, skip this step. We obtained the response curve from the validation flames. Let's go to the final results. They are of more interest to this community. We can mimic laminar flames with an accuracy that's within 0.01 of percentage, so 1% of the total mole fraction for the species. The temperature is within 40 Kelvin. And considering that these are measurements in enclosed combustor, this is a very good result. We're not using Rayleigh scattering, but directly ideal gas law to find it. Unfortunately, as in the interference region, so where possibly where is NH2, we have interference from the LF signal, and the accuracy, the precision in particular drops. And this is a work in progress. We still we have strategies to account for it, but still we're talking about 2% in terms of precision in standard deviation of our measurements. So we can say we demonstrated first quantitative measurements in laminar ammonia flames. The next step is try with turbulent flames. We did a more of a demonstration at this stage than an extensive campaign. We tested two cracking ratios, 14 and 28% of ammonia cracked. Reynolds number was fixed at 11,000, and we applied the simultaneous Raman and LF. These are preliminary results from the NO, and these are the results from the Raman. This is for the flame with 14% of cracking. At 11,000, we are about 40% of the blow-off Reynolds number. We can see evidence of localized extinction here. And this is comparing to the second turbine flame with 28 cracking ratio that, of course, has increased stability. Now, this is very new results. I got these plots literally this morning, but it shows that we can tackle turbulent flames. We can start answering those questions that Andrea pointed in the previous measurements and in the previous talk. And the idea is to extend it, of course, to more turbulent flames, trying to understand to answer the big question of combustion physics on ammonia. And again, I renewed the invitation for collaboration. So bring your burners to KAUST, and we can tackle it with this diagnostics that we have developed. Okay, that's all.
Thank you very much. So we'll move on to fourth speaker of the afternoon, who again is from KAUST. He is Dr. Ayman Elbaz, as a senior research scientist here in the CCRC. He obtained his PhD in mechanical power engineering from Helwan University in Cairo in 2008, and he has a Fulbright visiting assistance professor grant at the Faculty of Engineering, Vanderbilt University, USA. So he's going to talk to us about laminar flame speed measurements of ammonia blended with dimethyl ether.
Yeah, thank you.
Hello, everyone. My talk today is about laminar flame speed measurement of ammonia blended with dimethyl ethers. For the background, I think I have to go briefly with the background. Most of the background is already mentioned in the last talk. So decarbonization of energy sector depends on the availability of the renewable fuels. So these renewable fuels should meet the challenges associated with energy security from one side and minimizing the environmental effect of the energy generation process from the other side. I mean by energy security, we need to store and distribute a large quantity of energy. In this term, we can see the chemical storage in energy-dense fuel play or preferable for storing large quantities over a long time, and at the same time, you can widely distribute this energy. In contrast to that, we have the electric storage, which would provide like short and localized storage of energy. For this model, we can see that ammonia appears as a key energy carrier with the potential of application for low carbon energy storage and transportation and power generation. Okay, so if we look to this plot here, this is the ammonia. We plot the gravimetric density and volumetric density of ammonia relative to the other fuels. We can see that ammonia has a higher volumetric density relative to methane and relative to liquid hydrogen. And because of this, converting hydrogen into ammonia, it will make easy to transfer energy and store it for a long time. Ammonia has some advantages relative to hydrogen. It is 45% higher volumetric density relative to the hydrogen. It contains 17.6% by weight hydrogen. It is 30 times cheaper than the hydrogen per unit stored energy. And it can be liquefied at 8 bar in room temperature. Okay, this plot give us like a role of ammonia in the energy system overall. We can see here we can produce ammonia from fossil fuels, and with CO2 sequestration we can get a blue hydrogen, and then we can get ammonia. Or the other way, we can get ammonia from green hydrogen through the renewable resources. With the available well-structured infrastructure, we can store the ammonia, we can transport it using pipeline, or using ships or tankers. We can transport ammonia. And for utilization section, ammonia can be catalytically decomposed to form SOx-free hydrogen for production, or we can use ammonia directly in power generation and in internal combustion engines and the gas turbine. The question here is, do we need to make a modification in engine, or do we need a modification for the fuel? The answer, I think, yes, because ammonia has very different combustion properties compared to hydrocarbon. If you look here, this is the ammonia flame speed, laminar flame speed versus the equivalence ratio. It has very low flame speed, 7 centimeters per second relative to the other hydrocarbon fuels. Also, if you look to the extinction flame stretch rate, it has very low extinction stretch rate relative to methane flame. So the barriers of using ammonia is narrow flammability limit, low energy density, also higher ignition energy. And in terms of higher ignition energy, you can compare 930 K temperature compared to 859 for methane, and higher NO emissions. So one way to use ammonia is blending ammonia with highly reactive fuel is considered one way strategy to enhance the combustion characteristics of the ammonia. In this study, we blend ammonia with dimethyl ethers. Why dimethyl ether? Dimethyl ether can be produced from renewable resources. It has no carbon-to-carbon bond. It has oxygen content, low temperature of ignition. And you can see here, this is a flame with neat ammonia at 5 bar, equivalence ratio of 1. And the corresponding flame, when we blend the ammonia with 37% of DME, you can see that how fast the flame propagation in this condition. So the aim of this study is to characterize the combustion behavior of NH3 DME blend over a wide range of conditions by measuring laminar burning velocity. Also to improve and validate our recent past published model against new experimental data with ammonia and biofuels. This gives us like the experimental setup we are using to measure the flame propagation. We have a spherical vessel, and this spherical vessel is 330 mm inner diameter. And we are using a Schlieren setup to measure the flame propagation. And here, this is the running condition we covered in this study. So we start with 0 DME, X DME equals 0 means neat ammonia, up to 100% DME over a wide range of equivalence ratio for 3 initial pressure, 1, 3, and 5 bar. If we look here for neat ammonia, we can see the Lewis number. Lewis number for lean condition is less than unity, and it starts to increase when you get the mixture reaches. The same thing for the lower value of XDME in the mixture. However, if you go to the higher XDME, you can see the opposite trend of the Lewis number, and we will use this information to explain some behavior of the flame. So go to results. We have here, this is the stretch rate versus the unstretched laminar burning velocity. And this is for 1 bar case. And to the right, we have the cases for 5 bar cases for wide range of equivalence ratio to blending, like XDMA 1 and XDMA 0.37. We can see we have a linear trajectory between the unstretched flame speed with the stretch rate over a wide range of equivalence ratio. We have to mention here, we are limiting our measurement inside the vessel between RF flame radius of 15 up to 45 mm to reduce the effect of the overdriven ignition to the flame, and also to reduce the effect of the confinement of the vessel on our measurement. We have used nonlinear and linear extrapolation to extract the unstretched laminar burning velocity. And also we have here some information. We can say, if you look here for XDME equal 1, mean neat DME, we can see for rich condition, we have a sudden acceleration of the flame speed, and this is due to the development of the flame cellularity. Okay. Here, we would like to evaluate the sensitivity of this blend relative to the stretch rate, and this can be done through measuring the Markstein length. We can see here this equivalence ratio for the Markstein length for all the blend together with the neat ammonia data. We can see that there is 2 different trends. If we are talking about neat ammonia, we have a lower value of Markstein length, negative value for lean condition and start to increase. The same behavior we have it for low concentration of DME. But however, if you go to the higher XDME, we can see the Markstein length start to decrease. And we, for the same condition of the equivalence ratio, increasing the XDME, increasing the Markstein length, and this means we have more stable flames. If you go to the rich conditions, we have the opposite trend, where you are increasing the ammonia will stabilize the flame, and the flame instability is suppressed by adding ammonia in this regime. So this can give us like the flame appearance for pure ammonia at elevated pressure and equivalence ratio 1.2. We can see here the points effect affecting the flame propagation. Once you increase the XDME, we can see the flames start to be centered, and the flame radius take shorter time to get to the same flame radius. But however, we can see here start to form some cracks inside the flame. And these cracks is developed for flame cellularity at the pure DME, as we can see here. And this flame cellularity, we can see all of these flames from 0.18, the Lewis number is greater than 1. And this is caused by what we call hydrodynamic flame instability, which is functioning the expansion coefficient, and it's functioning the laminar flame thickness. So we simulate the laminar flame thickness. We can see the laminar flame thickness here for pure ammonia. It has a thick flame. When you increasing the XDME, the flames start to be thinner. Increasing the pressure, the flames start to be more thinner. And here, this is a thermal expansion coefficient. We can see for the rich mixtures, we have a thermal expansion coefficient big, and we have very small, thinner flame. And this can lead to the hydrodynamic flame instability. We observe it here for pure DME. So go to the laminar burning velocity. This plot showed the laminar burning velocity obtained for this model versus the equivalence ratio. This is the laminar burning velocity at 1 bar up to 5 bar. We can see the model we have reasonably detect the flame, the laminar burning velocity well over a wide range of equivalence ratio, and we obtain the maximum flame speed laminar burning velocity around equivalence ratio 1.1, increasing the pressure. The overestimation of the simulated results start to decrease here for 3 and 5 bar. And this plot shows the negative effect of the pressure on the laminar burning velocity we have. And to understand what is happening here, we add XDME. This is the sensitivity analysis of various XDME for stoichiometric mixtures for different blends, starting from 0.18 up to 0.47. We can see most of the reaction enhancing the flame speed is coming from the core of H2CO mechanism, which showing an increasing sensitivity with XDME. This means we have more radicals inside the flame. So the main H and OH producing channel are enhanced with XDME. However, the nitrogen family reaction shows a strong negative correlation on effect on the laminar burning velocity. And this plot showed the effect of the pressure. As we can see here, the same H and OH forming channels are suppressed at higher pressure. We can look to the H2 and CO core reflects this effect where we have a decrease in these radicals when we are increasing the pressure. Okay, we go to summary. It's just in this study, we tested the new blend of ammonia with DME as a biofuel, and the laminar burning velocity was found to increase with XDME. The laminar burning velocity obtained its maximum around equivalence ratio 1.1, and the predicted model reasonably catch the flame behavior. Markstein lens showed a decrease with the equivalence ratio for a given XDME, but for lower values of XDME and neat ammonia, we have the opposite trend. At elevated pressure and rich mixtures, the tendency of the flame instability is reduced by increasing the percentage of ammonia in the mixture due to increase the flame thickness and decrease the thermal expansion coefficient. Also, the reaction arising from H2 and CO mechanism showing an increased sensitivity with XDME. Most of the nitrogen family reactions show a strong negative effect on laminar burning velocity. I would like to also here to acknowledge this. This is a part of the work we are collaborating with Professor Amir Farouk and Binod Ghani to characterize the IDT for the same plant. And also we have Professor Fabian and Shrestha to do for developing the kinetic model for this study. Thank you.
Thank you very much. Thank you. Okay, that brings us to the last talk of the afternoon before the discussion session. And that is Professor Alessandro Stagni. He is Assistant Professor of Chemical Plants at Politecnico di Milano. He got his PhD in Industrial Chemistry and Chemical Engineering at Politecnico di Milano. And his research activity deals with chemical kinetic analysis of reacting systems of hydrocarbon and non-hydrocarbon fuels at different levels. So the development and reduction of chemical kinetic mechanisms and their application in CFD computations. And he's going to talk to us about an insight on ammonia chemistry, experimental and modeling challenges. Thank you.
Thank you very much for your nice introduction. And thank you for inviting me to this yearly conference. Today, I'm gonna talk about fundamental insights behind ammonia kinetics. And to do so, I will start with a short introduction. I wouldn't be so original discussing the importance of ammonia in the next generation combustion technology, because we all have heard a lot of motivations. So I will focus on the two triggers behind my research, which has been lasting, I think, 3 years, more or less. The first trigger is the increasing interest in ammonia as an energy vector. And energy carriers have been the matter of research of a European KAUST project called SmartCats, which ended 2 years ago. we started from a very well-known consideration. Ammonia is a potential platform molecule for energy storage and conversion, so to power the hydrogen economy. And due to the historical central role in the chemical industry, its production technologies were established. It is also used in combustion technology for controlling NOx emissions. The second trigger has been more industry-oriented, and it has been another European project ended last year called Improve. And the ultimate objective of this project was to drastically improve the energy efficiency of steam cracking furnaces by at least 20% in a cost-effective way, while simultaneously decreasing greenhouse gases emissions as well as nitrogen oxides. And to do so, we had to work on several aspects: the material, the design, the CFD modeling, and the alternative fuels. And as a partner of the project, we've been dealing with this last aspect. So the formulations and testing of the next generation biofuels. Biofuels are very attractive. They have a lot of advantages because from a life cycle perspective, they have zero net CO2 emissions. They can release us from fossil fuels, and we can recycle materials which would be wasted otherwise. So the question arising, okay, what is the importance of ammonia in this context? The problem is that biofuels often contain much more harmful compounds than fossil fuels. So sulfurated compounds, chlorinated, volatile organic compounds, and organic nitrogen. As a matter of fact, ammonia is often present in biofuels in trace amounts. The good thing is that we start from a consolidated point from a scientific point of view, because ammonia and in general nitrogenated fuels have been already studied from a chemical point of view since the 80s. Different reasons, but we already knew a lot. On the other side, there is an increasing trend in combustion in studying low temperature, diluted conditions, which were never explored during the 80s. Moreover, in the latest years, few studies have emphasized the effects of sensitization of ammonia on hydrocarbons, and this chemistry has been scarcely investigated also from a theoretical point of view. So we started our activity with a twofold purpose. From one side, studying the gas phase oxidation of ammonia, and second, studying the mutual interaction of ammonia with the higher hydrocarbons. And today I will be focusing on this first aspect. So let's start from the methodology for our studies. We performed a combined experimental and modeling study in collaboration with CNRS in Nancy, who dealt with the experimental parts. And in order to cover the whole temperature range, we used two different reactors. First of all, a Jet reactor, which is basically a spherical vessel where the fresh mixture is injected at the center and enters the reactor through 4 nozzles. And the high turbulence generated results in a homogeneous composition and homogeneous temperature, so that this can be modeled as a perfectly still reactor. In this way, we can explore the temperature range going from 500 to 1200 Kelvin, which is the mechanical resistance of the quartz material. Second, in order to explore also the high temperature regions, we completed our study with the use of a flow reactor. In this case, we have a tube made up of recrystallized alumina, specifically designed to approximate the segregated conditions so that we can model it as a plug flow reactor this time. A temperature profile is imposed to the reactor walls in such a way that in the isothermal region, we have a residence time of 50 milliseconds. The reactants and the products were identified and quantified with 4 complementary techniques. So first of all, online gas chromatography to quantify hydrogen during ammonia oxidation in the flow reactor. Second, the online mass spectrometry to identify ammonia, nitrogen, water, and oxygen still in the flow reactor. Third, a continuous wave cavity ring down spectroscopy shell, so the CW-CRDS, to quantify ammonia in the jet steam reactor. And last, a dual channel chemiluminescence NOx analyzer to quantify NO and NO2. The second cornerstone of our research has been the large-scale exploitation of theoretical kinetics. Why this? Because we wanted to reevaluate the key steps of ammonia reactivity, oxidation mechanism, since in the last, especially in the last couple of decades, we have done giant leaps in this direction. From an accuracy point of view, because right now we have a factor 2 of uncertainty in the kinetic race, which I can tell you is very, very low. Second, in terms of accessibility, because right now master equation calculations are accessible to an increasingly larger audience. And third, in terms of rapidity, thanks to the advances in information technology. But there are also a lot of troubles, because the evaluation of a single kinetic rate is actually a multi-step procedure, which is time-consuming, it is prone to error, and we need to make all of these as much as user-friendly as possible. How can we do this? We can do this with standardization and automatization. These were the cornerstones of a numerical tool known as S2KTP, which is the result of a collaboration between Politecnico di Milano and Argonne National Lab. This tool was developed in order to put all the steps for the evaluation of a single kinetic rate in a single workflow, just such to minimize the need of human intervention. So first, the ab initio phase with the evaluation of the potential energy surface, then the transition state theory phase, so the estimation of the kinetic rate, and finally, the master equation calculation. In this way, we can achieve a very, very high accuracy, so a factor 2, as I told you in the beginning, and we can minimize the need of human intervention. How can I say? The underlying principle is still the user-friendliness of the tool, so that we can reduce the need of knowledge from the users, although, okay, we still need to know the basics about the electronic structure and the kinetic theories. In this way, several reaction classes were implemented into S2KTP, and for our study, we particularly used the abstraction classes and the barrierless reactions. Finally, putting everything into a single kinetic mechanism. To do this, we used the underlying principles of the Polimi, the crack kinetic mechanism, especially the hierarchy and modularity. So we started from a core mechanism, which includes the basic species up to 3 carbon atoms, and this mechanism was recently revised in 2017, I seem to remember, and fully validated in a wide range of operating conditions. Then thermodynamics, then the NOx mechanism, since in 2019 we updated this package with the prompt and the reboarding mechanism, and finally the new model of ammonia, the ammonia mechanism, which we developed for this activity. Now let's have a deeper look on the results. First of all, by combining the uncertainty analysis and sensitivity analysis, we identified a subset of reactions which were supposed to be critical for our conditions. So initiation reaction, so the decomposition of ammonia through the breaking of the NH bond, the H abstraction by O2, the remaining H abstraction reactions, and finally the decomposition reaction of HNO into H and NO. And we found out several analogies with the existing kinetic rates, like ammonia decomposition on the top left, but also a lot of differences. For example, the H abstraction by O2. In this case, as you can see from the bottom left chart, we found the kinetic rate, which is below 1000 Kelvin, is 10 times higher than what is currently proposed in literature. And we will see that this will have a huge impact on our results. The same applies for HNO, where our proposed kinetic rate was very different from the state of the art, especially, again, in the low temperature conditions. So all of these results, all of this evaluation had a tangible impact on the performance of the mechanism. Let's start from the low temperature experiments in the jet reactor. In the considered conditions, you can see that the reactivity starts at around 1100 Kelvin for both 2% and 4% O2. And particularly compared to the literature mechanism, here I'm showing for simplicity only one of them, our mechanism is able to accurately predict the reactivity, while all of the other mechanisms have an earlier reactivity of about 100 Kelvin, which is a lot. On the other side, we started to ask ourselves, why is this happening? And the answer was provided by sensitivity analysis, as we can see in this chart. At low temperatures, you can see that the initiation reaction of ammonia, so ammonia plus O2, is actually slowing down the system. And this might sound a bit counterintuitive, an initiation reaction stopping the system. And then if we consider what happens at low temperature, everything becomes a bit clearer. Why this? Because at low temperatures, we have plenty of HO2, which is particularly stable. So when we have a lot of HO2, this reaction, which is affected by equilibrium, starts to feel the effect of the reverse reaction rate. And when we have a lot of products, so a lot of HO2, this reaction starts to reverse, starts to go in the reverse direction. And so instead of behaving as an initiation, it actually acts as a termination. And and we were able to identify this step only because the proposed reaction rate was 10 times higher than what is available in literature. Otherwise, we would go back to the other kinetic mechanism. And this is also confirmed by flux analysis in these two cases. As you can see, an ammonia plus O2, instead of giving NH2, it acts in the opposite direction. So NH2 plus HO2 gives ammonia. Second, the flow reactor experiments at higher temperature. The model here is reasonably able to capture the reactivity of ammonia. There is only a slight underprediction of the selectivity in terms of nitrogen. So nitrogen N2 over NO. But we have to remember that the purpose of our model is to be as general as possible. I mean, we want to work well, not only on our in-house data, but on a comprehensive data sets, not only made by ourselves. And when we perform sensitivity analysis on this N2 over NO ratio, you can see that the critical reactions are again those which we studied in the preliminary step. So HNO decomposition and H abstraction by O2, which in this case favors reactivity because we are at high temperatures, OH and H. Finally, mechanism generality, as I told you before. In order to assess the validity of the kinetic mechanism, we collected a huge set of experimental data sets from different facilities. So ignition delay time in shock tube and rapid compression machine, laminar flame speed, and speciation from flow reactor and burner stabilized flames. Results are pretty satisfactory, as you can see, and the mechanism behaves pretty well in the whole experimental range. We can say that the recalculated reactions are still the critical ones. In particular, for ignition delay time, we have that ammonia decomposition becomes important, especially at very high temperatures, which are the blue points. So let's go to the conclusions. From a chemical point of view, although ammonia is such a small molecule, this doesn't mean that it is easy to be investigated. And to do so, we use the multifaceted approach. So experimental, theoretical, and kinetic modeling. For the first aspect, we use a combination of two reactors to explore a wide range of temperature conditions. For the second, we used a recently developed ab initio tool to revisit the critical steps of the kinetic mechanism. And finally, the modular structure of the polyimide mechanism kind of eased our kinetic modeling. And in such a way, this work can serve as a consolidated starting point to extend our knowledge of ammonia in terms of sensitizing effects, and then for the further combination to interaction with higher hydrocarbons. Okay, before closing down, I would like to acknowledge the active contribution of my collaborators at the Crack Modeling Group, Professor Cavallotti, and the people at CNRS, so Olivier Binet, Frédéric Battel-Leclerc, and their PhD students, and the two project sponsors of my activity, Improve and Desmarkets. So thank you for your attention, and I will be open to questions during the final session.
Okay, thank you very much. So now, if we can get the all the speakers up, we'll have the question and answer session. So, is that? Yep, 1, 2. Yep, I'm getting there. Just give it a couple of minutes, gentlemen, while the others come back online, hopefully. She's not there. Yeah, I've got questions here. I'm just waiting for. We've only got 2 up.
Is there anybody else online?
Yeah. Okay. Right. Okay. We'll take that as being quorate then. Okay yeah. Then. Well, I'll ask. You have a question, Sam? We'll ask first.
Yes. Well, thank you all. This is a really interesting session. Now, my question is to Trevor about ammonia as a marine fuel. I mean, the targets of the industry is quite ambitious, not only in terms of retrofitting engines or even replacing engines, but also the whole infrastructure of refueling, which ammonia is not an easy thing to refuel from. And I was wondering if you have any views about how sort of feasible these targets are as sort of predicted, or at least as planned.
Sure. Well, I don't think that there is any technology roadblock. You say it's difficult to refuel with ammonia. There are 800 ammonia filling stations in Iowa. In Iowa, where we use ammonia as direct application fertilizer, a farmer with no training and no hazard experience takes a nurse tank to an ammonia fueling tank, fills it up, and drives it to his farm. And there are 800 such fueling tanks across Iowa. I find it implausible that we cannot do safe ammonia fueling, given that we can manage it with LNG. If you can refuel a ship with LNG, I think that you need to accept that fueling it with something that requires very sensible safety and training requirements. You need to be siting these things appropriately. There's no point dumping dangerous things in the middle of a highly populated area. But I don't see any technical or operational roadblock. The question really is do we want to decarbonize society?
No, I think you misunderstood my question. Well, the question is not, can we do it? Of course we can do it. The question is, will it be done on the time frame that's actually being suggested? That's my question.
It's an excellent question. I mean, we just finished the IMO's MEPC conference last week. They came out of it with, on the one hand, but on the other hand, kind of conclusions. And it's going to be a process of discovery. How aggressively regulators and policymakers support this kind of clean energy technologies. And it's not focused on ammonia. This isn't about, we need to be supporting ammonia. This is very simply, are we going to see political will to decarbonize? It's as simple as that. If we can support a portfolio of lower carbon solutions, that would be fantastic. There is absolutely no technological or operational hurdle to us doing this. It's feasible. We need to decide if we want to.
Okay, thank you very much. I know you missed my introduction of you. In that, I said that I spent quite a lot of my life championing methanol, which is a toxic liquid, obviously. So I wish you all the luck in the world with the toxic gas. Anyhow, I've got some questions online as well, so I'll move to one of those now. One was it's from an anonymous attendee, and they haven't told me who it's directed to. But the question is, do you have any plans to get a higher pressures for measuring laminar flame speeds? If so, how? So, yeah.
Okay. So I believe we don't have the plan to go to 10 bar for ammonia flames to measure the laminar burning velocity, because the flame speed will be very low if you get the trend with the laminar burning velocity with the pressure. You will see that the flame speed will be very low, and then the flame will be dominated by buoyancy effect. I think the better to get the correlation between the flame speed versus the pressure, and get the index of the pressure, and then you can expect how much the flame speed at 10 bar or any pressure.
Okay, thank you. Are there any other questions from the room now? I'll take one from the room if there are any. No, okay, I'll go back online. There's been some quite interesting questions that have been posed online, and they've been answered directly. So for the benefit of the attendees here, I might ask them again. So we had one question to Professor Stanier, and the question was, which reactions contain the most uncertainty? In other words, which reactions need to be recalculated or remeasured for better model prediction? So I think if you can answer that verbally. I know what you've written on the screen, sure. But nevertheless.
No, sure. Well, the answer is it depends on the way it's been estimated, because when we consider our kinetic rates in the kinetic mechanism, they might have been either experimentally measured or theoretically evaluated. And for both cases, it depends on the accuracy of experimental instrumentation and theoretical methods. It depends on the years, of course, because I mean, for example, for ammonia or in general nitrogenated species, there are two huge reviews of Dina and Bocelli 2000s and Bosch 2005, and over there the uncertainty of several of the reactions is reviewed. We recently, in 2020, we did a work of mechanism numerical optimization for ammonia, and we tried to answer in detail to this question. So, which is the uncertainty of each of the reaction rate? And so we tried to review all the theoretical methods according to which every reaction has been theoretically evaluated, and the same from an experimental point of view, because very often in the related papers the uncertainty is declared. So the answer is that there is not a single answer for this. but we need to dig into the source and find them out. Also, for most of we need to understand before that which are the critical reactions that we need to evaluate. For example, in our case, we found out that ammonia initiation via H abstraction by O2 was the critical one. And to our knowledge, it has never been studied theoretically until maybe a recent work of Professor Gruber 1 year ago. And that was a critical step, and we found out some degree of novelty in that. So my suggestion is let's do a synergistic interaction between chemical kinetics instrument like sensitivity analysis and flux analysis on one side, and on the other side, literature review to understand which is the uncertainty of the available rates.
Okay, thank you very much.
I guess a quick question.
Yes.
Okay, I was raising my hand, but I guess realize it's not easy to see.
Sorry, this is on.
Yeah, this is Hong.
Okay,
yeah,
online.
I would like to have a quick question as a DNS guide to the DNS presentation, Andrea. So it's very interesting. You showed a very nice images of low and high pressure with different lines of turbulent flames. It was not clear to me what you meant to say by the role of high diffusion of hydrogen, because the way I see it, the reaction at high pressure, the reaction rate is still confined to very narrow layer, especially with the ammonia. So the higher diffusion might actually push it into more like a so-called Peters thin reaction zone regime rather than distributed. So it was not clear to me what you implied and what you are actually showing. It was a kind of big image and with lots of wrinkles. So would you like to comment on that? What happens when you push the pressure high?
Yeah, so I apologize if this wasn't very clear in the in the slide. What I meant is that the local enrichment at the flame leading point that is created by the presence of hydrogen and by the fast diffusing of the hydrogen into the leading point, this was known from before. What it was not clear from before is that this effect is amplified at higher pressure beyond what one would expect by a linear scaling of the pressure. So the bottom line is that this leading points become strongly burning, and therefore they represent a very strong flamelet, if you want, that the turbulence doesn't manage to tear apart as it happens at the lower pressure. So in other words, even if these two flames were designed to be in the same place of the regime diagram, effectively they are not. I'm not sure if I made myself clear.
Yep, that's clear. Thank you very much.
Okay. Right. Question from Bassam.
Yeah, Bassam Dali. Andrea, I'm interested in your comment about differential diffusion. In this type of flames, you've got nitrogen on both sides, you've got oxygen, and then basically you have hydrogen diffusing in almost sort of homogeneous mix, or it's not homogeneous, but at least in its molecular weight. Now, you're suggesting that we should measure the differential diffusion. I guess as an experimentalist, once you go to higher pressure, your spatial resolution becomes limited. Your error bars, I think Gaetano has been brave to actually measure what he measured and show something sort of decent. I wonder what we learned from the DNS, and if why do you think we need to measure it also experimentally, knowing that it's simply hydrogen into
I didn't.
Next door should do.
Right. Yeah. So this is an interesting and difficult question. I mean, I wasn't implying that there is an established procedure, experimental procedure to measure the differential diffusion at this small scale. What I'm saying is that the cited work, or the work I cited from Princeton and Ed Lowe's group, this showed they call it extreme role of diffusion in hydrogen flames. There was no ammonia there. I mean, these were only lean hydrogen flames, right? But what that study lacks is pressure, the pressure trend, right? Because they focused on 10 atmospheres. In principle, you don't need to measure diffusion. What I was referring to is that the acceleration of the flame due to diffusion can be studied at different pressures, and trying to make pressure the only difference, and this is hard, I understand, I mean experimentally, right? Because when you increase pressure, you increase the density, so you increase the Reynolds number if your fans or whatever you use in these bombs do not, I mean, if the flow is the same, you, at everything else being equal, you change things that place these flames in different places in the regime diagram. On the DNS side, we are lucky, we can just design the case so that it's where we want to be nominally. So I don't know an answer to your question. I mean, it's a difficult problem, but I think it's needed, and it's not only about ammonia. I mean, my point was about hydrogen containing flames. The industry has been struggling, at least that I know of, since the mid 2000s when we were doing the first EU project with this, right? And one of the Siemens senior engineers concluded one of these projects, it was the end of 2009, I think, by saying, well, we designed a very good burner that works perfectly with 100% hydrogen at atmospheric pressure. As long as we go to 20 bar, things go awry, right? And I think that this is the explanation. This acceleration of the local enrichment has not been observed before, and therefore all of the empirical correlations that are used to scale the turbulent flame speed, they depend on the local laminar flame speed, right? And this is assumed that this is constant or roughly constant, and there are some adjustments that are proposed earlier, but these adjustments do not take into account pressure. So I think it's a very fundamental question that gives an answer not only to the ammonia, I mean, it's not specific to ammonia, but to hydrogen containing flames at large.
If I could follow up. So would you suggest then we take, say, hydrogen CO2, where the difference is quite big, and then be able to measure it? So in other words, would it make any difference?
No,
because
well,
what you want is its effect rather than...
Well, no, so what I mean is that one should be able to design an experiment where you have, when you increase the pressure, say from 1 to 10 atmosphere, your flame nominally is in the same place of the regime diagram. And this is tricky on the experimental side if you use one kind of sides of bomb or flame, right? It's not straightforward. So I don't know actually how you can do that, but and I don't think we have the time to find out now. But I think I think it's a hint, as I said, for the audience to stimulate your inventive of an experiment like the one from Ed Lowe, but that can achieve a scaling and maintaining the things, everything else being equal, you increase the pressure, right?
Easily said and done.
Yes. Everything else being equal, yeah. Okay, right. Well, let's. I'm going to ask a question that he's already answered online, but I think it's worth it for the sake of the room. There was a question to Professor Magnotti. It's about what are the possible challenges with using UV Raman spectroscopy for non-hydrocarbon flames? Can it be helpful in avoiding the interference from flame luminosity?
So I answered this already, but so UV, will you get, so first of all, flame luminosity is not an issue. The flames are luminous, but a microsecond shutter is sufficient to remove the luminosity. So it's not the main issue with this flame. The common issue with Raman scattering is if you have a laser-induced interference. So some fluorescent signal. In the case of methane flame, the common source was pH. That was the most common source of interference. In this particular case with ammonia, for this excitation wavelength, we found that NH2 was a main responsible. Actually, it could be a diagnostic by itself. But if you go in the UV, you're most likely going to excite even more species. So your interference will go up, most likely. I haven't tried, but there is no really a good incentive to try. You increase the Raman cross-section heavily, but then you have to rely on weaker power of the laser energy, and detectors, they are much less efficient. So overall, I don't foresee a huge benefit in going in the UV. There might be marginal benefit, but it's I'm not sure it's a good strategy.
Okay, thank you. Any other questions from the room at the moment? No. Okay. So I've got a question for Professor Stagni. It says, do you think there are parts of the kinetic mechanisms missing in detailed schemes?
Oh, okay. Yeah, I was going to reply in a brief way. Then we had a blackout here, Polytechnic. So now we are fine. So my opinion, my personal opinion is that for what concerns the reaction path, most of the knowledgeable has been kind of discovered. I'm not sure that there are further reaction paths to be included, but I'm quite sure that there is a lot to be perfectioned for several reaction paths. For example, I can make you a very clear example. It's the chemistry of H2NO. If you want, I can share the screen 1 second, and I can tell you what I'm meaning. So here, when we are dealing with the low temperature reaction path, there is this molecule H2NO, which is a critical crossroads in the low temperature decomposition of ammonia. But there is not so much accurately evaluated from a theoretical point of view, and most of the reactions of H2NO going towards HNO are the result of estimations based on analogies on other reactions. We can learn a lot, we can study a lot these low temperature reaction paths, and we can decrease the estimated uncertainty. Also in our mechanism, I mean, for what concerns these reactions, we use the analogies because there is not so, I mean, it's not also immediate to study them from a theoretical point of view, but there is plenty of room to improve these reaction paths.
Okay, thanks. Got a question for Professor Gruber. So it's regarding the volumes that you looked at in the mixture. Why did you select 40, 45, 15% ammonia, hydrogen, nitrogen in the mixture?
Sure. I was replying and typing, but it's because at the relevant conditions, so that is a preheat temperature of 750 Kelvin, and for equivalence ratio 0.45, which gives our target flame temperature, that is about 1800 Kelvin. This mixture has unstrained laminar flame properties, so speed, thickness, and temperature that are very similar to methane air flames at the same with the same flame temperature. So basically, it's because this ratio of ammonia hydrogen gives very similar properties to those of methane at the relevant conditions.
Okay, thank you. Any other questions in the room? No. Okay. Well, I'll ask the last question.
I had a question for the fellow panelists, if I may.
Yes,
I was intrigued by Bassam's question about whether, you know, my target dates for maritime uptake of ammonia were feasible and realistic. And I had a question, which is, what are the realistic feasible dates for, you know, these ammonia combustion technologies, for ammonia gas turbines, for, you know, we're doing a lot of theoretical analysis here. There's very, very interesting technology research being presented. When do we see the commercial product?
Okay, I can try to provide a feedback, if not an answer. I would say that it depends really on the customers. So the OEMs are ready to start a development path, but it takes time and money. I would say these things are related. You can accelerate, and I mean, if you pay more. And for internal combustion engines, I think it's possibly closer. It's a lower hanging fruit. However, it depends really on the performance you want to get out of it and on the emissions that you are ready to accept. But I think it's certainly feasible within the decade. That's my take. But and I mean, OEMs of internal combustion engines for ships have been saying that if somebody orders, I mean, some of them at least, that if somebody orders such an engine, they could develop it pretty quickly with some piloting of diesel or whatever, 1%.
Trevor, especially in the early session of today's conference it was exactly about that. There's actually 4 talks about gas turbines operating on ammonia. Some of them actually fully commercial. I could also tell you that we do have a 300 kilowatt ammonia gas turbine sitting in our lab that we're experimenting on. And Jamie may be able to tell you a little bit more about engines on ammonia. So commercial products are becoming available. You may have that MAN have a dual fuel engine with ammonia. So it is happening actually in parallel. But
well, almost all there seems to be this general consensus that 2024, 2025 is the year when products are going to be commercially available, having been, you know, initially piloted and demonstrated 23, 24. I'm just I'm you know, I like that timeline. I just wanted to get a sense of as you say, how feasible it is.
But some said something very important. So you can, so Mitsubishi has said that they have an ammonia gas turbine by 2025, I think, or something like that. But then when I asked them at the ASME conference last week or a couple of weeks ago, if this burner would be only for ammonia or for other fuels, then the answer was less clear. So, you know, I mean, if you want to buy a gas turbine that only burns ammonia, it's a bit tricky. A customer would like to have a backup fuel, the possibility of, you know, in the absence of ammonia, what do you do? And so that may take longer, I think, to have a burner that actually accommodates various fuels. So fuel flexibility, as Bassam said, it's a tall order in some cases.
Yeah, I think it's worth saying that we can probably burn ammonia acceptably. We have to target the emissions first, making sure that we can meet the emissions first with engines, and then once we can do that in the short term, then we'll look at increasing efficiency. Because basically, obviously, if you can't meet emissions, you can't sell, full stop. And from that point onwards, it becomes operating cost. But it does make you question whether there might not be better ways of converting ammonia. Maybe fuel cells, probably for the long run. But the technology needs developing as well. At least you then get past the slow flame speed problem by not having a flame. Yeah.
And emission is not just NOx, of course. It's it's ammonia itself, which is even worse. Yeah.
Yes.
But blending is another option that has been considered.
Yes.
Even in coal-fired boilers, ammonia is being added, although it has some effect on the soot formation.
Yeah. Okay. So, any other questions from the room or from panelists for anyone else? No? In that case, I think we will draw this session to a close. That'll give us 10 minutes break before the poster award-ish. I'll hand over to the organisers at that point, but we can draw this to a close now. I'd like to just thank all of the presenters, both up on the screen and in the room. So if we can give them all another round of applause, that would be good.